Something impossible happened on September 14th, 2015. For exactly 1/10 of a second, every atom in your body moved. Not from wind or vibration or heat. From something far stranger. A ripple in spacetime itself. A distortion in the fabric of reality that had been traveling toward Earth for 1.3 billion years finally arrived. It stretched you in one direction by less than the width of a single proton, then squeezed you in another direction, then released you. You never felt it. Neither did anyone else. But two machines, separated by 3,000 kilometers, both measured it happening at exactly the same instant. What those machines detected changed everything we thought we knew about the universe, because the signal they recorded should not have been possible. Not according to the man who predicted it would exist. Not according to most scientists who spent decades trying to build detectors sensitive enough to find it. Even after they succeeded beyond their wildest expectations, after they detected not one signal, but hundreds, the universe had one more surprise, waiting. On March 19th, 2025, when the 200th detection arrived, it came from black holes so massive they defied everything we understood about how black holes form. This is the story of how we learn to hear the universe singing in a language that doesn't use sound or light. How we discovered that reality itself can vibrate like a drumhead. And how what we heard rewrote physics, revealed the origins of gold, and proved that the cosmos is far stranger than we ever imagined. This is a story about listening to the universe in a language we never knew existed. About building instruments so sensitive they can measure changes smaller than an atomic nucleus across distances of 4 kilometers. About detecting collisions of objects so massive that when they merge, they convert 3 times the mass of our sun into pure gravitational energy in less than a second. It's about monster black holes, each weighing 100 times more than our star, spinning together at nearly the speed of light before they become one. But more than that, it's a story about patience, about building on ideas that sat dormant for decades, about scientists who believed in something invisible, something that Einstein himself doubted could ever be found. And it's about how, in September 2015, everything changed. How we learned to hear the universe singing. Tonight, let yourself drift into this cosmic symphony. Feel the weight of the day lift from your shoulders. Let your breathing slow, your thoughts soften. Because we're about to explore one of the most profound discoveries in the history of science, told not with urgency, but with wonder. A gentle journey through space-time itself, where reality bends, black holes dance, and the universe reveals secrets written in waves we cannot see, only measure. If these quiet explorations of cosmic mysteries help you unwind, if they give you a peaceful way to end your day with curiosity and awe, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. But for now, settle in, close your eyes if you wish, and let's begin this journey through the invisible architecture of the cosmos, through ripples in space-time that connect us to the most violent and beautiful events in the universe. Gravitational waves are not made of matter. They're not particles. They're not electromagnetic radiation, like light or radio waves. They're something more fundamental. They are ripples in space-time itself. The 4-dimensional fabric that Einstein showed us was the true stage on which everything in the universe performs. Imagine space not as empty nothingness, but as something that can bend, stretch, compress, and vibrate. When massive objects accelerate, particularly when they orbit each other or collide, they send waves through this fabric, like a stone dropped in a still pond sends ripples across water. But unlike water waves, these ripples travel at the speed of light, carrying information about their source across billions of light years. They pass through planets, stars, and galaxies without being absorbed or scattered. Nothing stops them. They simply continue, forever dimming but never stopping, witnesses to events of unimaginable violence occurring in the darkest corners of the cosmos. And when they finally reach Earth, when they wash over our small blue planet, they change the distance between objects by amounts so small that measuring them seems impossible. Yet, we have found a way to listen. The story of gravitational waves begins over a century ago, with a man working through equations in Berlin during the First World War, trying to understand gravity not as a force pulling objects together, but as the geometry of space-time itself. It continues through decades of doubt, through instruments that failed to detect anything, through scientists who were mocked for believing in fairy tales. And it crescendos in our present moment, where twice a week on average, detectors around the world register these cosmic whispers, each one telling us about black holes and neutron stars colliding in ancient times, in distant places, reshaping what we know about the universe. From the first detection in 2015 to the 200th in 2025, from black holes 30 times the mass of the Sun to monsters weighing 200 times more, from the discovery of neutron star collisions that forge gold and platinum to the promise of space-based detectors that will hear supermassive black holes merging at the centers of galaxies. This is a journey of discovery that is still unfolding. We stand at the beginning of gravitational wave astronomy, not the end. And tonight, we're going to explore it all, slowly, carefully, letting each revelation settle like snowflakes on still water. The 200th detection represents more than a number. It represents a transformation in how we study the universe. In the past, all astronomy was done with light, with electromagnetic radiation in all its forms, from radio waves to gamma rays. We built telescopes to gather ancient photons that had traveled for billions of years. But gravitational waves are different messengers. They're not blocked by dust or gas. They don't get absorbed. They carry information that light cannot, about the most extreme environments in the universe, about the strongest gravitational fields, about places where space-time itself is torn and twisted into shapes that defy imagination. Each detection is a glimpse into cosmic violence transformed into mathematical beauty. When two black holes spiral together, they don't explode. They don't emit light. They simply merge in a silent collision that releases more energy in a fraction of a second than all the stars in the visible universe combined. That energy escapes as gravitational waves, and when we detect them here on Earth, we can reconstruct the entire story. We can determine how massive the black holes were, how fast they were spinning, how far away the collision occurred, and even which direction in space it came from. All from measuring vibrations in space-time smaller than an atomic nucleus. Tonight, as you rest, know that gravitational waves are passing through you right now. They've been passing through everything, always, since the beginning of time. Black holes merging billions of light years away are sending their signals through your body at this very moment. Neutron stars colliding in distant galaxies are causing your atoms to oscillate by infinitesimal amounts. The universe is alive with these whispers, and only now, only in the last decade, have we developed ears sensitive enough to hear them. So let's journey together through this invisible landscape. From Einstein's desk in 1916 to the control rooms of LIGO in 2015. From the discovery of the first gravitational waves to the detection of the 200th. From understanding how these cosmic collisions work to exploring what they reveal about the nature of reality itself. And then we'll look forward to the future, to detectors 100 times more sensitive, to observatories in space, to discoveries we cannot yet imagine. The universe has been singing all along. We've only just learned to listen. And what we're hearing is more beautiful, more strange, and more profound than anything we could have predicted. Einstein's bold prediction, a century of doubt and wonder. In June 1916, as the Battle of the Somme began and the world tore itself apart in the Great War. A 37-year-old physicist in Berlin submitted a paper with a title that seemed utterly disconnected from the chaos around him. Approximative integration of the field equations of gravitation, it was called. Dry, technical, mathematical. And buried within its equations was a prediction that would take a century to confirm. A prediction that Einstein himself would later doubt. A prediction about ripples in the fabric of spacetime. Just 6 months earlier, Einstein had published his general theory of relativity, a complete reimagining of gravity not as a force, but as the curvature of spacetime caused by mass and energy. In Newton's universe, gravity was an invisible force that somehow reached across empty space to pull objects together. In Einstein's universe, there was no such force. Instead, mass and energy curved the geometry of spacetime itself, and objects simply followed the straightest possible paths through this curved geometry. It was like placing a bowling ball on a stretched rubber sheet. The ball creates a depression, and marbles placed nearby will roll toward it, not because the ball is pulling them, but because the shape of the sheet itself guides their motion. But Einstein's equations were notoriously difficult to work with. They were nonlinear, meaning that solutions didn't simply add together. The mathematics was complex, sometimes intractable. So Einstein did what physicists often do when faced with impossible equations. He made an approximation. He imagined a situation where spacetime was almost flat, just slightly disturbed from the perfect geometry of empty space. In this simplified scenario, he could linearize his equations, making them similar to the wave equations that describe light and sound. And that's when he discovered them. Solutions to his approximate equations that looked like waves. Ripples propagating through spacetime at the speed of light. When mass is accelerated, particularly when they moved in asymmetric ways, they would disturb the fabric of spacetime, and those disturbances would radiate outward in all directions. Just as an accelerating electric charge creates electromagnetic waves, light, accelerating masses would create gravitational waves. The prediction was elegant, even beautiful, but Einstein immediately recognized a problem. The waves would be incredibly, almost impossibly weak. Gravity itself is by far the weakest of the four fundamental forces. An ordinary refrigerator magnet can overcome the gravitational pull of the entire Earth when it holds a paper clip against a metal surface. If gravity is weak, gravitational waves would be weaker still. Einstein calculated that even the most violent events imaginable would produce waves so faint that detecting them seemed hopeless. Here's what's remarkable, though. Einstein was both right and spectacularly wrong. Right that the waves would be almost impossibly faint. Wrong that we could never detect them. But there's an even more surprising twist to this story. 20 years after predicting gravitational waves would exist, Einstein changed his mind completely. In 1936, he wrote a paper arguing that he'd made a mistake, that gravitational waves were merely mathematical artifacts with no physical reality. He was so confident in this conclusion that he submitted it to physical review, fully expecting publication. What happened next would embarrass one of history's greatest minds and nearly derail the search for gravitational waves before it truly began. Consider the numbers. When a gravitational wave passes through an object, it stretches space in one direction while simultaneously compressing it in the perpendicular direction. The amount of this stretch and squeeze is described by something called strain. For a gravitational wave from even a relatively nearby and powerful source, like two colliding black holes a billion light years away, the strain when it reaches Earth is on the order of 10 to the power of -21. That's a decimal point, followed by 20 zeros, and then a 1. It means that if you had two objects separated by the entire diameter of Earth and a gravitational wave passed through, those objects would move closer together and then farther apart by less than the width of an atomic nucleus. How do you measure something that small? In 1916, the answer was clear. You don't. You can't. It was, for all practical purposes, impossible. And Einstein, despite having predicted gravitational waves, didn't really believe they would ever be detected. He viewed them more as mathematical curiosities than physical phenomena that would ever be observed. They were real in the equations, but would remain forever hidden from human instruments. But there was another problem, one that would cause confusion and controversy for decades. When Einstein derived his wave solutions, he used a particular coordinate system, a particular way of labeling points in spacetime. And coordinates are somewhat arbitrary. You can describe the same physical situation using different coordinate systems, just as you can describe a location on an Earth using latitude and longitude, or using distance and direction from a specific city, or using any number of other systems. The question was, were gravitational waves real physical phenomena, or were they artifacts of Einstein's choice of coordinates? In 1922, Arthur Eddington, the British astronomer who had famously confirmed Einstein's prediction of light bending around the sun in 1919, made a remark that captured the skepticism. Eddington showed that of the 3 types of wave solutions Einstein had found, 2 were what we call gauge artifacts. They could be made to disappear or made to propagate at any speed, simply by choosing a different coordinate system. Eddington joked that these waves propagate at the speed of thought, because their properties depended entirely on how the physicist chose to think about the problem, not on any objective physical reality. This left only one type of wave, the transverse wave, which seemed to be coordinate independent. But even this raised suspicions. Einstein himself continued to wrestle with the reality of gravitational waves throughout his life. In 1936, 2 decades after his original prediction, he and his assistant, Nathan Rosen, wrote a paper arguing that gravitational waves could not exist in the full theory of general relativity. They submitted it to the journal Physical Review, confidently expecting publication. But something unexpected happened. The journal sent the paper to a referee for peer review. This was unusual at the time. Einstein was used to having his papers accepted without external scrutiny. The referee found an error in their mathematical reasoning and wrote a detailed critique. Einstein was furious. He withdrew the paper in a huff and submitted it to a different journal, vowing never to publish in Physical Review again. But his assistant, Nathan Rosen, had the mathematical integrity to look at the referee's comments carefully. And the referee, whoever they were, was right. There was an error in their reasoning. Einstein and Rosen reworked the paper completely, and when it was finally published in the Journal of the Franklin Institute, it came to the opposite conclusion. They titled it On Gravitational Waves, and argued that gravitational waves did exist after all. The fascinating twist? The anonymous referee was likely Howard Percy Robertson, a mathematician at Princeton who was one of the few people capable of checking Einstein's work. Einstein never knew who had corrected him, and he never learned that peer review, the process he'd found so insulting, had actually saved him from a major error. For decades afterward, the story of Einstein's rejection served as a cautionary tale about scientific humility. Even the greatest mind of the 20th century could be wrong, and even Einstein needed colleagues to check his work. The episode left Einstein skeptical about gravitational waves for the rest of his life. Though his equations clearly predicted them, though the mathematics was sound, he never seemed entirely convinced they were physically real. He would die in 1955, never knowing whether his century-old prediction would be confirmed. For all these struggles, for all Einstein's doubts, there was something undeniable in the mathematics. When you work with Einstein's equations properly, when you account for all the subtleties, gravitational waves emerge not as curiosities, but as inevitable consequences. Accelerating masses disturb spacetime, and those disturbances propagate. They are as real as electromagnetic waves, though far harder to detect. The question wasn't whether they existed in theory. The question was whether they existed in the measurable universe, and whether humans would ever develop technology sensitive enough to find them. The first glimmer of evidence came not from a direct detection, but from patient astronomical observation of an exotic object 21,000 light-years from Earth. In 1974, two radio astronomers, Russell Hulse and Joseph Taylor, were using the Arecibo Radio Observatory in Puerto Rico to search for pulsars, rapidly spinning neutron stars that emit beams of radio waves like cosmic lighthouses. They found one designated PSR B913 plus 16, but it was unusual. The timing of its pulses varied in a regular, periodic way. After careful analysis, they realized why. This wasn't a single pulsar. It was two neutron stars orbiting each other, and one of them was a pulsar whose signal we could detect. This was exactly the kind of system Einstein's theory predicted should emit gravitational waves. Two massive objects, each about 1.4 times the mass of the Sun, compressed into spheres just 20 kilometers across, orbiting each other at speeds approaching 300 kilometers per second. If general relativity was correct, this system should be losing energy to gravitational radiation, and that energy loss should cause the orbit to gradually shrink, bringing the two neutron stars closer together over time. Hulse and Taylor set out to measure this effect. They didn't detect the gravitational waves directly. That was still impossible with 1970s technology. Instead, they measured the orbital period with exquisite precision, tracking how long it took for the pulsar to complete one orbit around its companion. And they found that the orbital period was decreasing. The two neutron stars were spiraling together. They calculated the rate of energy loss based on the observed orbital decay and compared it to the prediction from general relativity for gravitational wave emission. The agreement was stunning. The observed orbital decay matched the theoretical prediction to within half of 1%. After just 4 years of measurements, they could say with confidence that this system was behaving exactly as it should if gravitational waves were carrying away energy. Over longer periods of observation, the agreement became even more precise. This binary pulsar system was an indirect but compelling proof that gravitational waves exist. It was strong enough evidence that Hulse and Taylor were awarded the Nobel Prize in Physics in 1993. But indirect evidence isn't the same as direct detection. We were watching the consequences of gravitational waves, seeing their effects on a distant system of neutron stars. But we weren't actually measuring the waves themselves as they passed through Earth. To do that would require instruments of unprecedented sensitivity, instruments that could detect changes in distance smaller than the nucleus of an atom. It would require decades of technological development, hundreds of millions of dollars, and a level of dedication that pushed the boundaries of what many thought was possible. The theoretical foundation was solid. Einstein had predicted gravitational waves. Hulse and Taylor had found indirect proof of their existence. But the direct detection remained elusive, seemingly impossible, a goal that some dismissed as quixotic. And yet, even as Einstein doubted, even as skeptics questioned, a small group of physicists in the United States began to imagine an instrument that might, just might, be sensitive enough to hear spacetime itself vibrate. They began to dream of LIGO. Einstein died in 1955, never knowing whether his prediction would be confirmed. The technology didn't exist. The funding didn't exist. The path forward was unclear, but the mathematics was beautiful, and the physics was sound. And sometimes that's enough. Sometimes a prediction sits quietly in the pages of journals, waiting not for years, but for generations, until the moment when human ingenuity catches up to theoretical insight. For gravitational waves, that moment was still decades away. But it was coming. The story of Einstein and gravitational waves is a reminder of how science works. It's not always a straight line from prediction to confirmation. Sometimes the journey is long, winding, full of doubts and detours, and debates that last decades. Sometimes the person who makes the prediction doesn't believe it themselves. Sometimes the proof takes 100 years. But the universe doesn't care about our doubts or our timelines. It simply is what it is. And spacetime, whether Einstein believed it or not, carries waves. Building LIGO. Engineering the impossible. There are some ideas so ambitious, so technically challenging, that when you first hear them, your immediate response is, "That's impossible." Building a detector sensitive enough to measure gravitational waves was one of those ideas. The requirements were staggering. You needed to measure changes in distance of less than 1/10,000th the diameter of a proton, across a span of several kilometers. You needed to do this while the Earth beneath you trembled with seismic vibrations, while temperature fluctuations caused everything to expand and contract, while passing trucks and ocean waves and even distant lightning strikes created noise in your instruments. You needed to build two identical detectors, separated by thousands of kilometers, so you could distinguish real gravitational wave signals from local disturbances. You needed vacuum systems large enough to remove all the air from spaces that stretched for 4 kilometers. You needed lasers stable enough to maintain their frequency to 1 part in a billion billion. You needed mirrors polished so perfectly that they wouldn't scatter light, suspended so carefully that they could swing freely enough to respond to gravitational waves, but isolated enough not to respond to local vibrations. And you needed to do all of this with a technology that had never been attempted at this scale, based on a physics principle that many still doubted would ever yield results. The dream of detecting gravitational waves with laser interferometry began in the 1960s and early 1970s with several physicists working independently. In the Soviet Union, Mikhail Gertzenstein and Vladislav Pustovoit proposed the basic idea. In the United States, Rainer Weiss at MIT published a detailed paper in 1972, analyzing how an interferometer could be used to detect gravitational waves and what sources of noise would limit its sensitivity. His paper included careful calculations of the required sensitivity, the design specifications, and even preliminary cost estimates. It was, in many ways, the blueprint for what would eventually become LIGO. An interferometer works by splitting a laser beam and sending the two halves down perpendicular paths, typically along 2 arms of an L-shaped structure. At the end of each arm is a mirror. The light bounces back and forth multiple times between mirrors, effectively increasing the length of the path it travels, and then the 2 beams are brought back together. When they recombine, they interfere with each other. If both beams have traveled exactly the same distance, they arrive in phase and reinforce each other. If one beam has traveled slightly farther than the other, they arrive slightly out of phase and partially cancel each other out. The key insight is this: a passing gravitational wave stretches space along one arm of the interferometer while simultaneously compressing space along the other arm. This changes the distance the light travels, creating a tiny difference in path length between the 2 beams. When the beams recombine, this difference shows up as a change in the interference pattern. By carefully monitoring this pattern, you can detect the passage of gravitational waves. But the devil, as they say, is in the details. And in this case, the details were diabolical. Consider just one of the many challenges: seismic noise. The Earth is constantly moving, vibrating with the rumble of distant traffic, the crash of ocean waves, micro-earthquakes, and countless other disturbances. These vibrations are typically on the order of micrometers or even millimeters. But gravitational waves cause displacements on the order of 10 to the power of -18 meters. That's a billion times smaller. How do you measure something so tiny when the ground beneath you is shaking a billion times more violently? The answer is isolation. Exquisite, multi-layered isolation. The mirrors in LIGO are not simply mounted on solid structures. They hang from sophisticated suspension systems designed to filter out vibrations. Imagine a pendulum. If you shake the support from which it hangs with rapid vibrations, the pendulum itself barely moves. High-frequency disturbances are naturally filtered out by the pendulum's inertia. But you need to filter low-frequency vibrations too. So LIGO uses not one pendulum, but a chain of them, each stage providing additional isolation. The final mirror hangs from a suspension system with 4 stages, each one absorbing more of the vibrations before they can reach the mirror. But that's just one problem. There are dozens more, each requiring ingenious solutions. Laser noise is another major challenge. Even the most stable lasers don't emit light at a perfectly constant frequency. Their output fluctuates slightly, and these fluctuations can mimic gravitational wave signals. To address this, LIGO uses a technique called power recycling, where mirrors are arranged to build up the laser power inside the interferometer, effectively increasing the strength of the signal. The laser that enters LIGO has a power of about 20 watts. By the time it's bouncing back and forth inside the instrument, the effective power is closer to 100 kilowatts. Then there's thermal noise. Everything at a temperature above absolute zero is vibrating at the molecular level. The mirrors in LIGO, despite being polished to near perfection, are constantly jiggling slightly due to thermal fluctuations. This is called Brownian motion, and it's unavoidable. The solution? Cool the mirrors, or use materials and coatings that minimize thermal noise. Advanced LIGO uses mirrors made of fused silica, a type of glass chosen for its low internal losses and ability to be coated with multi-layered dielectric coatings that reflect the laser light with minimal absorption. And perhaps most fundamentally, there's the quantum nature of light itself. At the most basic level, light is made of photons, and photons arrive at a detector randomly according to the laws of quantum mechanics. This creates what's called shot noise. The more photons you use, the less relative uncertainty you have in their number. But you can never eliminate this quantum uncertainty entirely. It sets a fundamental limit on how precisely you can measure the position of the mirrors. Advanced LIGO pushes up against this quantum limit, using techniques like squeezed light, where quantum correlations are manipulated to reduce noise in one measurement at the expense of increased noise in another. The scale of LIGO is almost hard to fathom. Each of the 2 facilities, one in Livingston, Louisiana, and the other in Hanford, Washington, consists of 2 arms stretching 4 kilometers in length. The arms are massive steel tubes, 1.2 meters in diameter, evacuated to a pressure 1 trillion times less than atmospheric pressure. Inside these tubes, the laser light makes many round trips, bouncing between mirrors that are among the smoothest surfaces ever created. If you were to scale up one of these mirrors to the size of North America, the largest imperfection would be less than 1 centimeter tall. The choice of locations was deliberate. You need 2 detectors separated by a large distance so you can confirm that a signal is real and not just noise in one instrument. The separation also allows you to determine the direction from which a gravitational wave is coming based on the slight difference in arrival time at the 2 sites. Light travels the 3,000 kilometer distance between Livingston and Hanford in about 10 milliseconds, so gravitational waves from different parts of the sky will arrive at the 2 detectors with different timing signatures. But even with 2 detectors in the United States, you can't pinpoint the source of gravitational waves very precisely. The sky localization from 2 detectors alone is relatively poor, often covering hundreds or thousands of square degrees. That's where the international network comes in. Virgo, a 3-kilometer interferometer near Pisa, Italy, joined the search in 2017. Kagura, a 3-kilometer detector in the mountains of Japan, came online in 2020. Together, this network of 4 detectors allows much better ski localization and provides crucial confirmation that signals are real. The development of LIGO took decades. A prototype 40-meter interferometer was built at Caltech in the early 1980s to test the basic principles. Throughout the 1990s, planning and construction advanced. The National Science Foundation committed what was, at the time, the largest single investment the agency had ever made in a physics project, eventually totaling over $1 billion when construction and operations costs were included. The initial LIGO detectors came online in 2002 and operated until 2010, searching for gravitational waves, but finding none. The technology simply wasn't sensitive enough yet, so they upgraded. Between 2010 and 2015, a major enhancement transformed initial LIGO into advanced LIGO, improving sensitivity by a factor of 10. New lasers, new optics, improved seismic isolation, better mirror coatings, and more powerful computers for data analysis. The upgrades were based on lessons learned from years of operation, on incremental improvements to each subsystem, on pushing every component closer to its theoretical limits. When advanced LIGO began its first observing run in September 2015, it represented the culmination of 40 years of development, from the earliest concepts to the most sophisticated gravitational wave detector ever built. The people behind LIGO are as important as the technology. Rainer Weiss, the MIT physicist who wrote that foundational 1972 paper, devoted much of his career to making gravitational wave detection a reality. Kip Thorne, a theoretical physicist at Caltech, contributed both scientific leadership and tireless advocacy for the project. Ronald Drever, an experimental physicist from the University of Glasgow who joined Caltech, developed many of the optical techniques that made LIGO's sensitivity possible. Barry Barish, also at Caltech, took on the role of principal investigator in the mid-1990s and transformed LIGO from a collection of brilliant individuals into a large-scale scientific collaboration capable of bringing the project to completion. Thousands of scientists, engineers, and technicians contributed to building and operating LIGO. People who spent careers developing better lasers, designing suspension systems, modeling noise sources, writing data analysis software, and tending the detectors day and night. It was a collective effort spanning decades, driven by a belief that the universe's most violent events were sending us messages written in the geometry of spacetime itself, and that we could, with sufficient ingenuity and persistence, learn to read those messages. There were moments of doubt, times when problems seemed insurmountable, times when critics questioned whether gravitational waves would ever be detected, whether the investment was justified, whether it might be better to spend the money on something with more certain returns. But the team persisted. They solved problems one by one. They improved sensitivity year by year. And in September 2015, as advanced LIGO began its first observing run with instruments 10 times more sensitive than initial LIGO, they were finally ready. Ready to listen to the universe in a new way. Ready to detect ripples in space-time. Ready to prove that Einstein's 100-year-old prediction, the one even he doubted, was not just mathematically beautiful, but physically real. And then, just 4 days into the first observing run, at 5:51 in the morning Eastern Time, on September 14th, 2015, the universe whispered, and LIGO heard. September 14th, 2015, the day everything changed. The chirp lasted only 1/10 of a second. That's all. 1/10 of a second of data. A brief pulse of signal buried in noise. A pattern of stretching and squeezing spacetime that swept through Earth carrying a story written 1.3 billion years in the past. But in that 1/10 of a second, everything changed. The era of gravitational wave astronomy began not with a gradual accumulation of evidence, but with a single, clear, undeniable detection. One moment we were hoping, theorizing, waiting. The next moment we were listening to the universe sing. The signal appeared first at the LIGO detector in Livingston, Louisiana. Then, 7 milliseconds later, it reached Hanford, Washington, having traversed the 3,000 kilometers between the two sites at the speed of light. The waveform was distinctive, rising in frequency and amplitude, like a chirp, starting around 35 Hz and sweeping up to 250 Hz before abruptly stopping. In the world of gravitational wave physics, this shape is unmistakable. It's the signature of two massive objects spiraling together, their orbital speed increasing as they lose energy to gravitational radiation, finally merging in a violent coalescence that shakes spacetime itself. The detection came at a moment both perfect and impossibly surreal. Perfect because it was so early in advanced LIGO's first observing run, just 4 days after the detectors went live, proving that the upgrades had worked beyond anyone's wildest expectations. But surreal because some scientists initially worried it might be a blind injection, a fake signal deliberately introduced into the data stream to test whether the analysis procedures could identify it. These blind injections were a standard part of commissioning, designed to keep everyone honest. Only a small group of people knew when they were happening, and they'd fooled the collaboration before. So, when Marco Drago, a postdoctoral researcher at the Max Planck Institute in Germany, saw the alert come through on his screen at 5:51 a.m. Eastern Time, his first thought wasn't, "We've made history." It was, "Is this real?" He began checking immediately. Was this a glitch in the data? Was someone testing the system? The signal appeared at both detectors, with the right time delay, 7 milliseconds, exactly what you'd expect for a gravitational wave crossing the United States at the speed of light. The waveform shape matched theoretical predictions. The frequency evolution followed the pattern expected from an in-spiral and merger. Everything looked right. Too right, perhaps. Could it really be this clean, this perfect, this early in the run? Word spread quickly through the collaboration. Other researchers began their own analyses, independently checking the signal, looking for any sign it might be artificial. Days turned into weeks. The tension built. Finally, confirmation came from the highest levels. This was not a blind injection. The signal was real. At that moment, everything changed. Word spread quickly through the LIGO scientific collaboration. Researchers began analyzing the signal in detail, using sophisticated algorithms to match the observed waveform against thousands of theoretical templates computed from Einstein's equations. The best match came from a binary black hole system, two black holes orbiting each other and merging. The larger black hole had a mass about 36 times that of the Sun. The smaller was about 29 times solar mass. Together, when they merged, they formed a single black hole of 62 solar masses. Wait, you might think, 36 plus 29 equals 65, not 62. Where did the missing 3 solar masses go? The answer is astonishing. During the final moments of the merger, as the two black holes spiraled together at speeds approaching half the speed of light, 3 times the mass of our Sun was converted into gravitational wave energy, according to Einstein's famous equation, E equals mc2. This energy radiated away in the form of ripples in spacetime, carrying information about the collision across the universe. By the time these ripples reached Earth 1.3 billion years later, they had weakened to the point where they changed the length of LIGO's 4-kilometer arms by less than 1/10,000th the diameter of a proton. The peak power output during the merger was extraordinary. For a brief moment, lasting only a few milliseconds, the gravitational wave luminosity, the rate at which energy was being radiated, exceeded the combined light output of all the stars in the observable universe. Not just all the stars in our galaxy, but all the stars in every galaxy we can see. The collision of these two black holes, for that fleeting instant, was the brightest event occurring in the cosmos, though not in light. In gravitational waves. The scientific team spent months analyzing the data, running countless checks to confirm the signal was real. They examined the noise characteristics of the detectors. They looked for correlations that might indicate instrumental problems rather than a genuine astrophysical signal. They tested the robustness of their parameter estimation, the process of determining the masses, spins, and distance of the black holes. Everything checked out. This was, beyond reasonable doubt, the first direct detection of gravitational waves from a binary black hole merger. But there was more. The detection wasn't just a confirmation of general relativity's prediction of gravitational waves. It was also the first direct evidence that binary black hole systems exist. Before this detection, the existence of stellar mass black holes in binary pairs was theoretical. We knew black holes existed. We'd found evidence for them through their effects on nearby stars and gas, but we'd never seen two of them orbiting each other. The detection proved not only that such systems exist, but that they can merge within the current age of the universe. On February 11, 2016, nearly 5 months after the detection, the LIGO scientific collaboration held simultaneous press conferences in Washington, D.C. and other cities around the world to announce the discovery. The signal was designated GW1fin50914, short for Gravitational Wave Detected on 2015, September 14th. The announcement was front-page news across the globe. Scientists, journalists, and the public grasped the significance immediately. A 100-year search had ended. A new field of astronomy had been born. David Reitze, the executive director of LIGO Laboratory, stood at the podium at the National Press Club in Washington and said simply, "Ladies and gentlemen, we have detected gravitational waves. We did it." The room erupted in applause. Later, Gabriela Gonzalez, the spokesperson for the LIGO scientific collaboration, added context. This detection is the beginning of a new era. The field of gravitational wave astronomy is now a reality. And Kip Thorne, one of LIGO's founders, reflected on the moment. It's the first time the universe has spoken to us through gravitational waves. Up until now, we've been deaf to them. The impact was immediate and profound. General relativity had passed yet another test with flying colors. The speed of gravitational waves matched the speed of light to extraordinary precision, as Einstein's theory predicted. The polarization of the waves, the way they stretched and squeezed space in two perpendicular directions, matched theoretical expectations. Even subtle effects like the ring down, the way the final black hole rang like a struck bell as it settled into its final state, were visible in the data and consistent with predictions from general relativity. But beyond confirming theory, the detection opened new questions. How do binary black hole systems like this form? Do they start as binary stars that both collapse into black holes and then spiral together over billions of years? Or do they form dynamically in dense stellar environments where black holes capture each other gravitationally? The masses of the black holes in GW1fin0914, particularly the 36 solar mass object, were larger than most stellar mass black holes previously known. This suggested that either stellar evolution can produce heavier black holes than we thought, or that some black holes might form through direct collapse without going through a stellar phase. The detection also demonstrated LIGO's capability beyond any doubt. Years of planning, decades of development, billions of dollars, thousands of person-years of effort had all led to this moment. The instrument worked. It could detect gravitational waves, and GW1fin0914 was just the beginning. During the first observing run, which lasted from September 2015 to January 2016, LIGO detected 2 more binary black hole mergers. During the second observing run in 2017, they found several more, including the first detection of a binary neutron star merger. In October, the Nobel Prize in Physics was awarded to Rainer Weiss, Kip Thorne, and Barry Barish for decisive contributions to the LIGO detector and the observation of gravitational waves. The recognition came swiftly, just 2 years after the first detection, a testament to the significance of the achievement. But as the laureates themselves emphasized, the prize represented the work of hundreds of scientists over decades. It honored not just 3 individuals, but an entire collaboration, an entire field, an entire journey from theoretical prediction to experimental reality. GW109 transformed gravitational waves from an abstract prediction into concrete data. We could now see the waveforms, study their properties, compare them to theoretical models. We could learn about black holes in ways that had never been possible before. With electromagnetic astronomy, we could study black holes only indirectly, through their effects on nearby matter. But gravitational waves gave us direct access to the black holes themselves, to their masses, spins, and orbital parameters. We could watch them spiral together, merge, and settle into their final state, all encoded in the stretching and squeezing of spacetime. The chirp that swept through Earth on September 14, 2015, was a voice from the distant past. A message about black holes colliding when the universe was less than 5/6 its current age. It had traveled for 1.3 billion years, through expanding space, past galaxies and stars and dust, never absorbed or scattered, never stopped, carrying its information at the speed of light until it reached our small planet. And there, in 2 L-shaped buildings separated by 3,000 kilometers, lasers flickered and mirrors moved and computers recorded the signal. After 100 years of theoretical work, after 40 years of technological development, after decades of hope and doubt, we had finally heard the universe whisper. And the universe, it turned out, had much more to say. GW1150914 was just the first word in a much longer story. A story that would include hundreds more detections, monster black holes with masses exceeding 100 suns, neutron stars colliding and forging gold, and revelations about the cosmos that continue to reshape our understanding. The day everything changed was not an ending. It was a beginning. The universe had been singing all along. We had just learned, finally, to listen. Understanding black hole collisions, a cosmic dance. To truly grasp what gravitational wave detectors are hearing, you need to understand the dance itself, the choreography of black hole collisions that produces these ripples in spacetime. It's a process that unfolds over billions of years, compressed into a signal that sweeps across our instruments in seconds or fractions of seconds. It's a story of gravity at its most extreme, of objects so dense that they distort spacetime into knots, of energies so vast they dwarf anything we experience on Earth. Black holes are, in a sense, the universe's final punctuation mark on massive stars. When a star much more massive than our Sun, perhaps 20 or 30 or even 100 times as massive, exhausts its nuclear fuel, it can no longer support itself against its own gravity. The core collapses catastrophically in a supernova explosion, and if enough mass remains after the explosion, that mass continues collapsing past the point where even neutron degeneracy pressure can halt it. The result is a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. The defining feature of a black hole is its event horizon, the boundary beyond which escape is impossible. Outside the event horizon, you could still theoretically escape if you had enough speed. But at the horizon and below, spacetime itself is so warped that all paths lead inward. The curvature is infinite in the sense that it points only toward the center. Time and space become strangely intertwined. If you were to cross the event horizon, moving radially inward would be like moving forward in time. You couldn't reverse it, any more than you could travel backward in time. But black holes aren't simply empty voids in space. They have properties. They have mass, obviously, the amount of matter that collapsed to form them. They have angular momentum, spin, because the collapsing material carried rotation with it. And according to general relativity, that's essentially all they have. The so-called no-hair theorem states that black holes are completely described by just three numbers: mass, spin, and electric charge. Everything else about the material that formed them, its composition, its original structure, is hidden behind the event horizon. Black holes, in this sense, are remarkably simple objects, despite being formed from the most complex and violent processes. Now imagine two black holes in orbit around each other, a binary black hole system. How does such a system form? The most straightforward scenario involves a binary star system, two massive stars born together and orbiting their common center of mass. Over millions of years, both stars exhaust their fuel, explode as supernovae, and leave behind black holes. If the binary survives both explosions, which isn't guaranteed, you're left with two black holes orbiting each other. But there's another possibility. In dense stellar environments, like the cores of globular clusters, where stars are packed much closer together than in typical regions of the galaxy, black holes can capture each other gravitationally through what are called dynamical interactions. A black hole passing near another might exchange energy and momentum with nearby stars in complex three-body or four-body interactions, eventually becoming bound into a binary. These dynamically formed binaries might have different properties than binaries formed from stellar evolution, such as more random spin orientations. Regardless of how they form, once you have two black holes orbiting each other, the story proceeds in three distinct phases: in spiral, merger, and ring down. Let's walk through each one, slowly, carefully, watching how spacetime itself responds to this cosmic dance. The in-spiral phase begins when the two black holes are still far apart, orbiting each other with periods that might be hours or days. As they orbit, they emit gravitational waves, and those waves carry energy away from the system. It's a slow process at first. The orbit gradually shrinks as energy is lost, and as it shrinks, the orbital speed increases. This leads to a runaway effect. As the orbit tightens, the gravitational wave emission grows stronger because it scales with the orbital frequency. Stronger emission means faster energy loss, which means the orbit shrinks faster, which increases the frequency more, and so on. Over millions, or even billions of years, the orbit steadily decreases. The black holes spiral closer and closer together. For most of this time, gravitational wave detectors on Earth couldn't see them. The frequencies are too low, the amplitudes too small. But eventually, as the black holes close to within a few hundred kilometers of each other, their orbital frequency enters the sensitivity range of ground-based detectors like LIGO and Virgo. That's when the signal appears. In the data, the in-spiral looks like a chirp, a tone that rises steadily in both frequency and amplitude. The orbital frequency is related directly to the gravitational wave frequency, which in turn determines the pitch of the sound you'd hear if you converted the signal to audio. As the black holes spiral closer, they orbit faster, and the pitch rises. Meanwhile, as they get closer to Earth's detectors in terms of the phase of their orbit, the amplitude of the waves increases, because the acceleration of the masses is growing. The chirp gets louder and higher pitched, like a cosmic slide whistle rising toward an inevitable climax. For a system like GW-15094, with black holes of 29 and 36 solar masses, the signal sweeps through LIGO's sensitive frequency band in about a tenth of a second. The black holes complete about 10 orbits during this time, each orbit faster than the last, their speeds reaching significant fractions of the speed of light. At the end of the in-spiral, just before the merger, the two black holes are moving at roughly half the speed of light and are separated by only a few hundred kilometers. The gravitational field is so strong that space-time around them is wildly distorted, bent into shapes that defy intuition. Then comes the merger phase. The two event horizons touch, In a sense, the black holes are no longer separate entities. They plunge together, their horizons merging into a single, larger event horizon. This is the moment of maximum energy release. In GW 1.0914, 3 solar masses of energy were radiated away in a few milliseconds during this phase. The merger itself is chaotic, violent in a way that's hard to visualize. The spacetime around the colliding black holes is twisting, oscillating, radiating energy in all directions. If you could somehow watch it happen from a safe distance, you'd see not just the black holes, but the very geometry of space around them warping and folding in on itself. The gravitational wave signal during the merger reaches its peak amplitude. This is the loudest moment, the strongest signal, the time when LIGO's mirrors experience the maximum displacement. It's also the most complicated part of the waveform. During the inspiral, the signal follows relatively simple patterns that can be calculated using post-Newtonian approximations. Expansions of Einstein's equations in powers of the orbital velocity divided by the speed of light. But during the merger, no such approximations work. The gravitational fields are too strong, the velocities too high, the curvature too extreme. To understand merger waveforms, physicists rely on numerical relativity, solving Einstein's full field equations on supercomputers. These simulations are incredibly computationally demanding, requiring teams of researchers months or years to develop and run. But they've been successful. By 2015, numerical relativity had advanced to the point where accurate waveforms could be computed for a wide range of black hole masses and spins. These simulated waveforms form templates against which observed signals could be matched, allowing scientists to extract physical parameters like mass and spin from the data. Finally, after the merger comes the ring-down phase. The newly formed black hole is not initially in equilibrium. It's distorted, aspherical, oscillating like a struck bell. These oscillations are called quasi-normal modes, and they're a characteristic property of black holes, determined entirely by the black hole's mass and spin. As the black hole oscillates, it radiates gravitational waves, gradually dissipating the distortion energy. The oscillations damp out exponentially, and the black hole settles into a stable, stationary state described by the Kerr solution, the unique solution of Einstein's equations for a rotating black hole in isolation. The ring-down signal has a characteristic frequency and damping time. By measuring these, physicists can test whether the final object is indeed a black hole, described by general relativity. So far, every detected ring-down has been consistent with the predictions for a Kerr black hole. This is a powerful test of general relativity in the strong field regime, where spacetime curvature is immense and no approximations are valid. The theory passes with flying colors every time. Throughout all 3 phases, the gravitational waves encode information. The rate at which the frequency increases during inspiral depends on the masses of the black holes. The total mass determines the frequency scale of the entire signal. The mass ratio influences subtle features in the waveform, as does the spin of each black hole. By carefully analyzing the signal, matching it against theoretical templates, physicists can determine these parameters with impressive precision. For GW 1.0914, the analysis revealed masses of 36 and 29 solar masses for the initial black holes, with a final black hole mass of 62 solar masses. The spins were moderate, not extremely high or low. The distance to the source was estimated at 1.3 billion light-years, determined from the amplitude of the signal and the inferred masses. Even the orientation of the binary's orbital plane relative to the line of sight could be partially constrained from the polarization of the waves. But there's something profound to contemplate here. When we detect these signals, we're not seeing light from the event. Black hole mergers don't produce light. They're dark events, invisible to telescopes. The only reason we know about them at all is because they disturb spacetime. They send ripples through the fabric of reality, and those ripples, traveling at the speed of light, eventually reach us. We're not looking at the merger. We're feeling spacetime itself shake. The energy scales involved are staggering. 3 times the mass of the sun converted to gravitational wave energy in less than a second. If you could somehow convert 3 suns into pure energy and release it all at once, that's what you'd get. The total energy is approximately 5 times 10 to the power of 47 joules, or about 5,000 foes in the jargon of astrophysics, where 1 foe equals 10 to the power of 51 ergs. For comparison, a supernova releases about 1 foe. This merger released 5,000 times more energy than a supernova, almost all of it in gravitational waves rather than light. And yet, despite this tremendous energy release, by the time the waves reached Earth, they were so weak that they displaced LIGO's mirrors by less than 10 to the power of negative 18 meters. That's why detecting them is so hard. The universe's most violent events become whispers by the time they reach us. But whispers, it turns out, are enough. With sensitive enough instruments, with careful enough analysis, we can hear them. And from those whispers, we can reconstruct the entire story. 2 black holes, dozens of times the mass of our sun, spiraling together over eons, finally merging in a collision that shook spacetime across billions of light years. Every black hole merger tells a slightly different story. Heavier black holes produce lower frequency signals. Lighter ones produce higher frequencies. If the spins are aligned with the orbital angular momentum, the signal has certain characteristics. If they're misaligned or even counter-rotating, the waveform changes. Some mergers happen head-on with minimal orbital motion before collision. Others involve hundreds of orbits slowly decaying. The variety is enormous, and each detection adds to our understanding of how black holes behave, how they form, and how common they are in the universe. As we'll see, some black hole mergers push into entirely new territory. Monster black holes with masses exceeding 100 times that of the sun. Black holes in the so-called mass gap, a range where conventional stellar evolution theory predicts no black holes should form, and even hints of black holes that might have merged not once, but multiple times, growing larger with each collision in a process called hierarchical merging. The cosmic dance of black holes is rich, varied, and endlessly fascinating. But for now, understand this. When you hear about gravitational wave detections, what's really being detected is spacetime itself vibrating. It's not a metaphor, it's literal. The fabric of reality is oscillating, stretched, and squeezed by events occurring vast distances away. And we've learned to listen. We've learned to decode these oscillations, to extract from them the stories of black holes dancing in the dark, merging in silent collisions, radiating energy that crosses cosmic voids to whisper their secrets to our instruments. In this way, we've become not just observers of the universe, but listeners to its deepest rhythms, to the fundamental music of gravity itself. The 200th detection, a new era of discovery. On March 19, 2025, when the 200th gravitational wave candidate of the current observing run was logged, the announcement wasn't made with the same fanfare as the first detection. There were no press conferences, no Nobel Prizes on the immediate horizon, no front-page headlines declaring the discovery to the world. And yet, in its own quiet way, the 200th detection was just as significant as the first. It represented a transformation from hope to routine, from discovery to survey, from asking "can we" to asking "what can we learn?" The signal came at 0725 local time and was detected by both LIGO observatories, while COGRA was offline for maintenance. It appeared to originate from a binary black hole merger approximately 15 billion light-years away, an astounding distance representing more than twice the separation of GW 0914. 3 researchers from the University of Trieste in Italy were on shift at that moment: David Di Piero, Giuseppe Troian, and Agata Travato. Their job was to validate the event and notify the scientific community, a task they performed within minutes. The notification went out through NASA's General Coordinates Network and other alert systems, reaching astronomers around the world almost immediately. The speed of this process is worth appreciating. Within about 30 minutes of the gravitational waves passing through Earth, the Rapid Response Team had analyzed the signal, estimated the masses of the merging black holes, determined the approximate location in the sky, and shared this information publicly. This rapid dissemination enables multi-messenger astronomy, the coordinated observation of cosmic events using different types of signals. Although most black hole mergers don't produce light and therefore don't offer electromagnetic counterparts to observe, the system is in place for events that do, like neutron-star mergers. But let's step back and understand what the 200th detection really means in context. To do that, we need to look at the history of gravitational wave observations. When advanced LIGO began its first observing run in September 2015, the team had modest expectations. They hoped to detect perhaps a few events per year. During the first run, which lasted from September 2015 to January 2016, they detected 3 binary black hole mergers: GW150914, GW151126, and LVT51012. Just 3 events in about 4 months of observing time. The second observing run started in November 2016 and continued through August 2017. During this period, LIGO detected 7 more black hole mergers and 1 binary neutron star merger, GW170817, which we'll discuss in detail later. The third observing run was split into 2 parts: O3A from April to October 2019, and O3 BAT from November 2019 to March 2020. By the end of O3, the total number of gravitational wave detections across all observing runs had reached 90 events. 90 events detected across about 23 months of cumulative observing time between September 2015 and March 2020. That was the state of gravitational wave astronomy when the third observing run ended, interrupted by the COVID-19 pandemic. 90 collisions of black holes and neutron stars, each one representing a cosmic event of incredible violence, each one telling us something about the population of compact objects in the universe, each one a data point in understanding how these systems form and evolve. Then came O4, the fourth observing run, which began in May 2023. And this is where the numbers change dramatically. In the first 23 months of O4, from May 2023 to April 2025, the LIGO-Virgo-Cagra collaboration detected 200 gravitational wave candidates. That's more than double the total from all previous runs combined, detected in roughly the same amount of time. The rate of detection has skyrocketed. Why the dramatic increase? Several factors contribute. First, the detectors themselves have been upgraded between runs. Advanced LIGO now operates with improved sensitivity thanks to enhancements made during the break between O3 and O4. These include better isolation systems, improved coatings on the mirrors, more powerful lasers, and the implementation of squeezed light, a quantum technique that reduces noise. The result is that the detectors can see farther into the universe, reaching more distant sources and therefore observing a larger volume of space. Second, the network has expanded. Virgo in Italy joined the observing run after a short break in early 2024, adding a crucial third detector to the network. Cagra in Japan, though still in its early stages of operation and not yet at full sensitivity, participated for about a month in 2023. Even with limited participation, the presence of multiple detectors improves the ability to confirm events and localize them in the sky. Third, and perhaps most importantly, Gravitational waves are more common than initially expected. The universe is full of merging black holes. They're forming, evolving, and colliding at rates that surprised even optimistic predictions. Every few days, somewhere in the observable universe, two black holes spiral together and merge. The signals from these events, weakened by cosmic distance but still detectable, arrive at Earth regularly, sometimes multiple times per week. Of the 200 events detected in 2004, the vast majority involve black hole mergers. Binary black hole systems dominate the catalog, with masses ranging from a few times the mass of the Sun to over 100 solar masses. Neutron star mergers remain relatively rare in the detected population. This isn't because they're intrinsically less common, but because they produce weaker signals. Neutron stars are less massive than black holes, so their mergers emit gravitational waves with lower amplitude. They're harder to detect unless they occur relatively nearby. There's also a growing number of what are called mass gap objects detected in 2004 data. The mass gap refers to a puzzling region between about 3 and 5 solar masses, where very few compact objects have been found. This gap exists because the most massive neutron stars are thought to be around 2 to 2.5 solar masses, while the lightest black holes formed from stellar collapse should be at least 5 solar masses. Objects in between are rare and don't fit neatly into our models of stellar evolution. Yet, gravitational wave detectors are finding them, challenging our understanding of how these compact objects form. Each detection follows a similar process. The gravitational wave passes through the detectors, causing minute changes in the lengths of the interferometer arms. Automated search algorithms, running continuously, scan the data stream for patterns consistent with gravitational wave signals. When a candidate is identified, it's given an initial assessment. Is this likely to be astrophysical or could it be noise? The rapid response team, consisting of over 600 researchers spread across different time zones, is immediately alerted. The RRT members on duty examine the candidate in detail. They check the data quality flags to ensure the detectors were operating properly at the time of the event. They look at the signal's consistency between detectors. They run parameter estimation algorithms to infer the properties of the source: masses, spins, distance, sky location. Within about 30 minutes, they make a preliminary classification. Is this a binary black hole, a binary neutron star, or something else? What's the false alarm rate? The probability that this signal arose from random noise, rather than a real astrophysical event? This information is then shared with the astronomical community through rapid alert systems. For most black hole mergers, there's little follow-up to be done because they don't produce light. But for neutron star mergers or other events that might have electromagnetic counterparts, the rapid alerts allow telescopes around the world to point their instruments at the estimated sky location and search for the corresponding transient signal. This is the promise of multi-messenger astronomy, using gravitational waves to trigger follow-up observations in electromagnetic wavelengths, combining the information from both messengers to learn more than either could reveal alone. The 200th event, detected on March 19, 2025, was likely a binary black hole merger located about 15 billion light-years away. At that distance, the collision occurred when the universe was significantly younger, providing a glimpse into the population of black holes in the early cosmos. The analysis is still ongoing as researchers refine their estimates of the masses, spins, and other parameters. But even without final numbers, the detection adds to the growing statistical picture of black hole mergers across cosmic history. What are we learning from this flood of detections? Several key insights have emerged. First, binary black hole systems are common. They're not rare exotica, but a regular feature of the universe. Second, the mass distribution of black holes is broader than expected. We're finding black holes much heavier than typical stellar remnants, suggesting either that stellar evolution can produce more massive black holes than we thought, or that some black holes grow through multiple mergers. Third, the spins of merging black holes vary widely, providing clues about their formation channels. Some have spins aligned with their orbital angular momentum, consistent with formation from binary stars. Others have misaligned spins, suggesting dynamical capture in dense stellar environments. Fourth, the rate at which black holes merge has implications for the growth of supermassive black holes. If stellar mass black holes can merge repeatedly, building up mass over time, this hierarchical growth might contribute to the formation of the million and billion solar mass black holes found at the centers of galaxies. Gravitational wave observations of intermediate mass black holes, those with masses between 100 and 100,000 solar masses, provide crucial evidence for this pathway. Fifth, gravitational wave detections are testing general relativity in regimes never before accessible. Each merger provides a new opportunity to check whether the observed signals match Einstein's predictions. So far, every test has confirmed general relativity. The speed of gravitational waves matches the speed of light to extraordinary precision. The polarization of the waves is consistent with theory. The way black holes ring down after merging matches the predicted quasi-normal modes. General relativity continues to pass every test with flying colors. The achievement of 200 detections in a single observing run is a testament to the maturity of gravitational wave astronomy. What was once a dream, then an experimental challenge, then a hoped-for discovery, is now a regular observational tool. Gravitational wave detectors have become astronomical observatories in their own right, comparable to optical telescopes or radio dishes in their ability to survey the cosmos and reveal new phenomena. Yet, we're still early in this journey. The current detectors, though remarkably sensitive, are not the final word. Upgrades are planned that will push sensitivity even further. A+ configurations for LIGO, enhanced versions of Virgo, improvements to Kagra, all designed to reach deeper into the universe and detect weaker signals. And beyond these incremental improvements, plans are underway for entirely new detectors. Third-generation ground-based observatories with 10 times the sensitivity of current instruments and a space-based detector that will open an entirely new frequency range. The 200th detection is a milestone, but it's not a destination. It's a marker on a road that continues into the future, toward thousands of detections per year, toward a complete census of compact object mergers across cosmic time, toward understanding not just individual events, but the statistical properties of entire populations. From the first chirp in September 2015 to the 200th signal in March 2025, the field has transformed, and the transformation is far from over. In the quiet early morning hours of March 19th, when spacetime rippled and detectors responded, and researchers on shift validated yet another event, there was no fanfare, but there was satisfaction. The satisfaction of routine success, of a scientific field that has matured from uncertainty to confidence, from rarity to abundance, from question to answer. The universe is speaking, and we are listening. 200 times over, and counting. Monster black holes, pushing the boundaries. Not all black hole mergers are created equal. While the typical events detected by LIGO involve black holes of a few dozen solar masses, occasionally the detectors register something unusual, something heavier, something that shouldn't exist according to conventional theories of stellar evolution. These monster black holes, weighing 100 times more than our sun, or even more, are pushing the boundaries of what we thought was possible and forcing astrophysicists to reconsider how black holes form and grow. The story of monster black holes begins with a signal detected on May 21st, 2019 at 0302 UTC. It appeared in the data from both LIGO detectors and Virgo, A short burst of gravitational waves lasting only about 1/10 of a second. The signal was designated GW19521, and from the moment scientists began analyzing it, they knew it was special. The frequency of the signal, peaking at only about 60 Hz, was lower than typical black hole mergers. Lower frequency means higher mass, and when the analysis was complete, the results were stunning. The larger of the two merging black holes had a mass of approximately 85 times that of the Sun. The smaller was about 66 solar masses. Together, when they merged, they created a final black hole of 142 solar masses. About 8 solar masses of energy were radiated away as gravitational waves during the collision. But it wasn't just the total mass that made GW19521 remarkable. It was where those masses fell in the theoretical landscape of black hole formation. According to well-established models of stellar evolution, there's a range of masses where black holes should not form directly from collapsing stars. This forbidden range is called the pair instability mass gap, and it extends roughly from 65 to 120 solar masses. The physics behind this gap is fascinating and somewhat counterintuitive. When an extremely massive star, one with an initial mass of perhaps 130 to 250 times the mass of the Sun, reaches the end of its life, the core becomes so hot that photons in the core gain enough energy to spontaneously create electron-positron pairs. This process, called pair production, removes energy from the photon field that would otherwise support the star against gravity. The result is a sudden loss of pressure support. The core collapses catastrophically, triggering explosive burning of oxygen and silicon. But instead of forming a black hole, the entire star is blown apart in what's called a pair instability supernova. Nothing is left behind. No remnant, no black hole. The star is completely disrupted. For this reason, standard stellar evolution theory predicts that black holes in the mass range from about 65 to 120 solar masses should not exist. They can't form from the collapse of single stars. Yet, the primary black hole in GW190521 had a mass of 85 solar masses, right in the middle of the forbidden range. And the final merger product, at 142 solar masses, was also solidly in a region where direct stellar collapse shouldn't produce black holes. The detection was the first clear evidence for an intermediate mass black hole, a black hole with a mass between 100 and 100,000 solar masses. Before this, intermediate mass black holes were theoretical objects, suspected to exist based on indirect evidence, but never definitively observed. How can black holes form in the mass gap if stellar evolution forbids it? The most likely explanation, based on what we currently understand about black hole dynamics, involves hierarchical merging. The process would work something like this. Imagine two smaller black holes, each formed from stellar collapse, and each with a mass below the gap, say 40 and 50 solar masses. They orbit each other, emit gravitational waves, and eventually merge, creating a black hole of roughly 90 solar masses. This 90 solar mass black hole now sits in the gap, but it didn't get there by stellar collapse. It got there by merger. Now, if this 90 solar mass black hole happens to be in a dense stellar environment, like the core of a globular cluster or a nuclear star cluster near the center of a galaxy, the pattern could continue. It might encounter another black hole and form a new binary. Over time, this second binary also merges, creating an even more massive black hole. Through a series of mergers, the evidence suggests black holes can build up mass step by step, populating regions of the mass spectrum that direct stellar collapse can't reach. GW190521 provided the first strong evidence for this process. The 85 solar mass primary was likely itself the product of an earlier merger, and the 142 solar mass final black hole could, in principle, merge again with yet another black hole, growing even larger. This hierarchical growth might be one of the pathways by which supermassive black holes, the monsters at the centers of galaxies with masses of millions or billions of suns, are seeded and grown. But GW990521 wasn't the end of the story. In November 2023, during the fourth observing run, LIGO and Virgo detected an even more massive merger, designated GW231123. This event produced a final black hole of approximately 225 solar masses, created by the coalescence of black holes with masses around 100 and 140 solar masses. Both progenitors were themselves likely products of earlier mergers, and the resulting 225 solar mass object is one of the most massive stellar mass black holes ever detected. The black holes in GW311123 were also rapidly spinning, near the maximum allowed by Einstein's theory of general relativity. A spinning black hole drags space-time around with it in a phenomenon called frame dragging. There's a limit to how fast a black hole can spin, set by the requirement that the event horizon remain a closed surface. Beyond this limit, the black hole would be naked, its singularity exposed, which most physicists believe is impossible. The spins measured in GW311123 were close to this maximum, suggesting the black holes had undergone previous mergers that spun them up. These monster black holes challenge our understanding in multiple ways. First, where do they form? Hierarchical mergers require that black holes stay in environments where they can repeatedly encounter and capture other black holes. This likely means dense stellar systems like globular clusters or the centers of galaxies. But globular clusters are relatively small and don't contain unlimited black holes to merge. At some point, you'd expect the black holes to either merge with everything available or be ejected from the cluster by gravitational interactions. Second, how do the spins evolve? When two black holes with aligned spins merge, the resulting black hole also spins, typically faster than either progenitor. But if multiple mergers occur with different spin orientations, the final spin could be lower. Understanding the spin distribution of massive black holes provides clues about their merger history and the environments in which they formed. Third, what's the rate of these massive mergers? GW190521 occurred at a distance of about 17 billion light-years, comb-oving distance accounting for cosmic expansion, making it one of the most distant events ever detected. GW231123 also came from cosmological distances. If such massive mergers are relatively common across the history of the universe, they could contribute significantly to the growth of black hole populations and might explain some puzzles about intermediate mass black holes. There's also the intriguing possibility of electromagnetic counterparts. Most black hole mergers don't produce light because black holes themselves don't emit radiation. And if they're isolated in empty space, there's nothing for them to interact with. But if a merger occurs near a supermassive black hole, perhaps in an accretion disk surrounding the central black hole of a galaxy, the merger could disturb the disk and produce a flare of light. And here's where the story takes an unexpected turn. For GW990521, astronomers reported something that shouldn't have been possible: a possible optical transient, detected by the Zwicky Transient Facility, a survey telescope in California. The transient appeared in the right region of the sky and at roughly the right time. If this connection is real, and that's still a matter of scientific debate, it would represent the first electromagnetic signal ever detected from a black hole merger, an event we've always assumed would be completely dark. The proposed scenario reads like science fiction made real, the merger happening inside or near the accretion disk of a much larger, supermassive black hole. When the two smaller black holes merged, the resulting 142 solar mass black hole received a kick due to asymmetric gravitational wave emission, much like how a rocket gains momentum by expelling exhaust. This kick could have sent the new black hole careening through the surrounding gas of the accretion disk, creating a shockwave and heating the gas until it radiated light. However, the association remains uncertain. The localization of gravitational wave sources is not precise enough to definitively link them to specific optical transients, especially when the uncertainty region spans hundreds of square degrees of sky, an area equivalent to thousands of full moons. Follow-up observations and careful modeling are needed to determine whether the optical signal was truly related to GW19E0521, or just a chance coincidence. The possibility, though, is tantalizing enough that astronomers continue to search for similar events. Monster black holes also raise questions about the future. As more and more mergers occur, as black holes continue to hierarchically grow, where does it end? In dense stellar clusters, eventually, the largest black holes either merge with everything available or get ejected through gravitational slingshot interactions. But in the cores of galaxies, near supermassive black holes, the environment might continually replenish the supply of black holes through stellar evolution and dynamical capture. Over billions of years, this could lead to a population of very massive stellar mass black holes, possibly even bridging the gap between stellar mass and supermassive black holes. The discovery of intermediate mass black holes through gravitational waves has profound implications for understanding the seeds of supermassive black holes. How did the billion solar mass black holes observed in quasars at high redshift, when the universe was less than 1 billion years old, grow so large so quickly? One possibility is that they started from larger seeds than we previously thought. If intermediate mass black holes form through hierarchical mergers or direct collapse of primordial gas clouds were common in the early universe, they could grow to supermassive sizes more quickly than if they started from stellar mass seeds. Every detection of a monster black hole adds to this puzzle. With each massive merger, we learn about the upper end of the black hole mass distribution, about the efficiency of hierarchical growth, about the astrophysical environments where these processes occur. The statistics are still relatively small, just a handful of events. But as more years of observations accumulate, as detectors become more sensitive and can reach farther into the universe, the sample will grow. And with it, our understanding of how black holes populate the universe across all mass scales. In many ways, monster black holes represent the frontier of gravitational wave astronomy. They're at the edge of what current detectors can reliably detect, requiring highly sensitive instruments and sophisticated analysis techniques. Their signals are brief, sometimes just a few cycles, making parameter estimation challenging. But precisely because they're pushing the boundaries, they're teaching us things we didn't know, revealing phenomena that textbooks said shouldn't exist, forcing us to expand our theories and consider new possibilities. The universe, it seems, is more creative than we imagined. It has found ways to build black holes in mass ranges that simple stellar evolution says should be empty. Through the dance of gravity, through the patient accumulation of mergers over cosmic time, it has sculpted objects that challenge our understanding and inspire our curiosity. And gravitational waves give us the ability to detect these monsters, to study them, to trace their origins and evolution. From the 85 solar mass primary of GW190521 to the 225 solar mass final remnant of GW231123, we're witnessing a population of black holes that redefine what's possible. A population that exists not despite physics, but because of it. Because gravity, given time and opportunity, can build wonders beyond our initial imagination. Neutron stars and multi-messenger astronomy. On August 17, 2017, at 12:41:04 UTC, something extraordinary happened. Not just the detection of gravitational waves that was becoming routine by then, but the detection of gravitational waves and light from the same event. For about 100 seconds, LIGO and Virgo observed a signal unlike any they'd detected before. The frequency was higher, the duration longer, sweeping through the instrument's sensitive band like a sustained note rather than a quick chirp. And then, just 1.7 seconds after the gravitational waves stopped, the Fermi Gamma Ray Space Telescope and the International Gamma Ray Astrophysics Laboratory detected a short gamma ray burst, a brief flash of high-energy light coming from the same region of sky. The race was on. Gravitational wave detectors had pinpointed the source to a region of about 30 square degrees in the constellation Hydra, near the galaxy NGC 4993, about 130 million light-years away. Within hours, telescopes around the world swiveled to point at this region. Optical telescopes, infrared telescopes, radio telescopes, X-ray observatories. Everyone who could observe joined the search. And 11 hours after the gravitational wave signal, astronomers spotted it. A new point of light in NGC 4993 that hadn't been there before. The optical transient was designated 8/2017 GFO, but it would become known simply as the kilonova, the long-predicted but never before observed explosion that occurs when two neutron stars merge. The event, designated GW-Sun 0817, was not just a gravitational wave detection. It was the dawn of multi-messenger astronomy with gravitational waves. For the first time, a cosmic event was observed in both gravitational waves and electromagnetic radiation, combining two completely different types of signals to tell a more complete story than either could alone. Over the following days and weeks, observatories on 7 continents and in space monitored the aftermath, watching as the kilonova evolved, as its spectrum changed, as different wavelengths brightened and faded. By the time the observations were compiled, 70 observatories had contributed data, making GW-Sun 0817 one of the most intensely studied astronomical events in history. To understand what made this event so special, we need to understand neutron stars. These are the remnants of massive stars that weren't quite massive enough to form black holes. When a star with an initial mass of about 8 to 20 times that of the Sun exhausts its nuclear fuel, it explodes as a supernova. But unlike the most massive stars, whose cores collapse all the way to black holes, these intermediate mass stars leave behind a core that stabilizes as a neutron star. A neutron star is matter compressed to densities that defy everyday intuition. Take 1.4 times the mass of the Sun and squeeze it into a sphere just 20 kilometers in diameter. The density is about 400 trillion times that of water, or roughly the density of an atomic nucleus spread across a macroscopic object. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. The gravity at the surface is so strong that if you could somehow stand there, you'd be crushed by a gravitational field 200 billion times stronger than Earth's. The interior of a neutron star is exotic beyond description. The outer layer, just a few meters thick, is a rigid crust of iron and other nuclei. Below that, as density increases, neutrons drip out of nuclei and form a neutron-rich fluid. Deeper still, in the core, the conditions are so extreme that we don't fully understand what form matter takes. It might be a superfluid of neutrons, a soup of quarks, or something even more exotic. The uncertainty in the equation of state, the relationship between pressure and density in neutron star interiors, is one of the biggest open questions in nuclear physics. When two neutron stars orbit each other, they emit gravitational waves, just like black holes do. But the signal is different because neutron stars, unlike black holes, can be deformed by tidal forces. As they spiral closer, each neutron star raises tides on the other, pulling the matter into an elongated shape. This tidal distortion depends on how stiff or soft the neutron star matter is, which in turn depends on the equation of state. By measuring the tidal effects encoded in the gravitational wave signal, physicists can constrain the properties of ultra-dense matter. The gravitational wave signal from GW17C0E17 lasted much longer than typical black hole mergers. Because neutron stars are less massive, they spend more time in LIGO's sensitive frequency band before merging. The detector observed about 3,000 complete orbits over those 100 seconds, compared to just 10 or so orbits for a black hole merger like GW100914. This longer signal allowed for much more precise determination of parameters. The masses of the two neutron stars were measured to be about 1.4 and 1.6 times the mass of the Sun, consistent with the known population of neutron stars. But gravitational waves told only part of the story. What happened after the merger? When the neutron stars collided, they didn't immediately form a black hole. Instead, they likely formed a hypermassive neutron star, an object supported temporarily against gravitational collapse by rapid rotation and possibly magnetic fields. This object was unstable, but for a brief time, measured in fractions of a second, or perhaps a few seconds, it existed as the densest, hottest concentration of matter in the present-day universe outside of black holes. Eventually, the hypermassive neutron star collapsed, likely forming a black hole, but not before some of the neutron-rich matter was ejected into space. This ejected material, traveling at a significant fraction of the speed of light, carried with it an extraordinary cargo: heavy elements forged in the intense neutron flux of the merger. This is where the kilonova comes in. For decades, astrophysicists had wondered where the universe's heaviest elements came from. Elements heavier than iron are not produced in normal stellar fusion. They require neutron capture processes, where atomic nuclei absorb neutrons faster than they can beta decay, building up heavier and heavier isotopes. There are two main neutron capture processes: the S process, slow, which occurs in certain stars over long time scales, and the R process, rapid, which requires an intense, sudden neutron flux. The R process is responsible for about half of all elements heavier than iron, including elements like gold, platinum, uranium, and most of the rare earth elements. But where does the R process occur? For years, supernovae were considered the most likely site, but detailed models showed that typical supernovae don't produce the right conditions. The neutron-to-proton ratio isn't high enough. The temperatures aren't quite right. Another site was needed. Neutron star mergers fit the bill perfectly. In the aftermath of the merger, as neutron-rich material is ejected, the conditions are ideal for the R process. The material is incredibly neutron-rich, having come from the interiors of neutron stars. It's heated to billions of degrees by the merger, and it expands rapidly into space, allowing the newly synthesized elements to cool and stabilize. The kilonova is the visible result of this process. As the ejected material expands and cools, the freshly synthesized radioactive isotopes decay, releasing energy. This energy heats the expanding cloud, causing it to glow. The color and brightness of the glow depend on the composition of the ejecta. Material with lighter R process elements, those with atomic masses around 100, produces a blue or ultraviolet glow. Material with heavier elements, particularly lanthanides with atomic masses around 140 to 170, produces a red or infrared glow because lanthanides have complex electron shells that absorb light efficiently, making the material more opaque. Observations of AT2017 GFO showed both components. Initially, the kilonova was blue, suggesting lighter elements. Over the next few days, it evolved to redder wavelengths, indicating the presence of heavier elements. The total mass of heavy elements ejected was estimated at about 0.05 solar masses, or roughly 50 times the mass of Earth. Of that, approximately 10 Earth masses consisted of gold and platinum alone. But here's where this story becomes deeply personal, where cosmic violence connects directly to your life. Think about that for a moment. Every gram of gold in existence, in jewelry, in electronics, in dental fillings, in the device you might be holding right now, was forged in the collision of neutron stars billions of years ago. Not in ordinary stars, not in supernovae. In the violent merger of objects so dense that a teaspoon weighs 1 billion tons, objects that spin hundreds of times per second, and whose surfaces have gravity fields 200 billion times stronger than Earth's. When ancient neutron stars merged somewhere in the distant universe, they scattered these elements across space in a cloud of radioactive debris, moving at a significant fraction of the speed of light. Eventually, that material mixed with interstellar gas. It drifted, it cooled, it joined other clouds, and billions of years later, it was incorporated into the molecular cloud that collapsed to form our solar system. The gold in a wedding ring, the platinum in a catalytic converter, the rare earth elements in electronics, all of it passed through a colonnova. All of it traveled for eons before ending up here, on Earth, shaped by human hands into objects of utility and beauty. GW 170817 confirmed neutron star mergers as a primary site for the R process. This resolved a long-standing mystery and provided a concrete production mechanism for about half the periodic table. But the event revealed even more. About 9 days after the merger, X-ray emission was detected from the source. About 16 days after, radio emission appeared. These emissions grew brighter over the following months, revealing the presence of a relativistic jet, a narrow beam of material moving close to the speed of light. The jet was likely powered by the accretion of material onto the newly formed black hole. As matter fell in, it released energy, some of which was focused into jets perpendicular to the accretion disk, similar to the jets seen in quasars and some supernova. The short gamma-ray burst, detected 1.7 seconds after the gravitational waves, was likely emission from this jet. However, the jet was not pointed directly at Earth. We observed it from an angle, which is why the gamma-ray burst was relatively weak, and why the X-ray and radio emission took days to become visible. The study of GW 170817 involved an unprecedented level of international collaboration. Within minutes of the gravitational wave detection, alerts went out to thousands of astronomers. Observatories that had clear skies immediately began searching. Within hours, dozens of telescopes had detected the kilonova. Over the following weeks, data poured in from around the world and from space. Optical spectra showed the fingerprints of heavy elements. Infrared observations tracked the cooling of the ejecta. Radio data revealed the jet structure. X-ray observations constrained the central engine. The scientific output was staggering. On the day of the official announcement in October 2017, dozens of papers were published simultaneously. 8 letters appeared in the journal Science, 6 in Nature, and over 30 in the Astrophysical Journal Letters. Nearly 100 preprints were posted on the RXIV, the online repository for scientific papers. The event had an immediate and profound impact across multiple fields: gravitational wave physics, nuclear astrophysics, relativistic jets, cosmology, and nucleosynthesis. One of the most exciting results came from combining gravitational wave and electromagnetic observations to measure the Hubble constant, the rate at which the universe is expanding. Gravitational waves provide a distance measurement independent of the cosmic distance ladder. The amplitude of the gravitational wave signal, combined with the inferred masses of the neutron stars, tells you how far away the source is. Meanwhile, electromagnetic observations identify the host galaxy and provide a redshift measurement, telling you how fast the galaxy is receding due to cosmic expansion. Dividing redshift by distance gives the Hubble constant. This method, called the standard siren approach, yielded a Hubble constant value of about 70 kilometers per second per megaparsec, consistent with other measurements but with large uncertainties due to having only one event. As more neutron star mergers are detected, this method will improve, potentially helping resolve a current controversy in cosmology, where different measurement techniques give slightly different values for the Hubble constant. GW-SYN 170817 also tested general relativity in new ways. The nearly simultaneous arrival of gravitational waves and gamma rays, with only a 1.7-second difference over a travel time of 130 million years, demonstrated that gravitational waves travel at the speed of light to within 1 part in 10 to the power of 15. This is an extraordinarily stringent test of a fundamental prediction of Einstein's theory. If gravitational waves had a mass, even an incredibly tiny one, they would travel slightly slower than light. The observations ruled out even the smallest masses for a hypothetical graviton, the quantum particle associated with gravity. The event also allowed tests of gravitational wave polarization. General relativity predicts that gravitational waves have 2 polarization states, analogous to the 2 polarization states of light. Alternative theories of gravity predict additional polarizations. By analyzing the signal seen at 3 detectors, LIGO and Virgo, and comparing it to theoretical expectations, physicists confirmed that the observed polarization matched general relativity's predictions. No evidence for extra polarizations was found, though sensitivity to such effects is still limited. Perhaps most importantly, GW-SYN 170817 demonstrated the power of multi-messenger astronomy. By observing the same event in gravitational waves, gamma rays, X-rays, ultraviolet, optical, infrared, and radio wavelengths, scientists could piece together a comprehensive picture. Gravitational waves revealed the inspiral and merger, providing masses and the nature of the objects, the gamma ray. Burst showed the formation of a relativistic jet. The colonnova revealed nucleosynthesis and the ejection of heavy elements. The X-ray and radio afterglow traced the jet's interaction with surrounding material. Each messenger added information the others couldn't provide. Since GW-SYN 170817, additional neutron star merger candidates have been detected, though none with an electromagnetic counterpart as clear and compelling. The rarity of multi-messenger events involving neutron stars is partly because such mergers are less common than black hole mergers, and partly because detecting an electromagnetic signal requires the merger to be relatively nearby and to occur with favorable viewing geometry. But the promise remains. Every future neutron star merger, detected by gravitational waves, triggers a coordinated global effort to search for light. And when the next multi-messenger event occurs, it will add to the story, refining our understanding and potentially revealing new phenomena. GW-SYN 170817 was more than a detection. It was a moment when multiple branches of astronomy and physics converged. It was a demonstration that the universe's most extreme events can be studied not just with one type of signal, but with all the tools at our disposal. It was a proof of concept for a new way of doing astronomy, one where gravitational waves and light work together, where international collaboration happens on timescales of hours, where theoretical predictions from nuclear physics and general relativity are tested against observations from dozens of instruments. It was, in many ways, the fulfillment of a vision that had guided astronomers for decades: to observe the cosmos with all our senses, to combine messengers, and to understand events more completely than ever before. And it reminded us, once again, that we are made of stardust, not just metaphorically, but literally. The atoms in our bodies, the calcium in our bones, the iron in our blood, the iodine in our thyroid, were forged in stars and scattered by their deaths. Some through supernovae, some through stellar winds, and some, perhaps even the gold in that wedding ring, through the collision of neutron stars that sent ripples through spacetime and scattered treasure across the cosmos. What gravitational waves reveal about reality. Beyond the specific stories of individual collisions, beyond the discovery of black holes and neutron stars merging in the distant past, gravitational wave detections have a deeper significance. They are not merely data points in a catalog of cosmic events. They are tests of fundamental physics, probes of reality itself at its most extreme. They allow us to ask and begin to answer questions about the nature of spacetime, the behavior of gravity in the strongest possible fields, and the architecture of the universe on the largest scales. Start with general relativity itself. Einstein's theory, published in 1915, revolutionized our understanding of gravity, but testing it rigorously has always been challenging, especially in regimes where gravitational fields are strong. Near Earth, where gravity is weak, alternative theories of gravity often make predictions nearly identical to general relativity. The differences show up only when fields become intense, when space-time curvature is large, when velocities approach the speed of light. Binary black hole mergers provide exactly such conditions. When two black holes orbit each other in their final moments before merging, space-time around them is wildly distorted. The curvature is immense. The orbital speeds reach significant fractions of light speed. Nonlinear effects, where gravity affects itself, become important. This is the strong field, highly dynamical regime where general relativity's predictions differ most strongly from alternative theories. And every gravitational wave detection is an opportunity to test whether the observed waveforms match Einstein's predictions. So far, general relativity has passed every test. The frequency evolution of the waveforms during in-spiral matches, the post-Newtonian approximations, derived from Einstein's equations. The shape of the merger signal matches numerical relativity simulations based on those same equations. The ring-down frequencies of the final black hole match the quasi-normal modes calculated from the Kerr solution. The polarization of the waves, the way they stretch space in perpendicular directions, matches the two polarization states predicted by general relativity. No deviations have been found. This doesn't mean general relativity is the final word. We know the theory is incomplete. It doesn't incorporate quantum mechanics. It predicts its own breakdown at singularities inside black holes and at the Big Bang. Dark matter and dark energy, which together make up 95% of the universe's mass energy, are mysterious additions not explained by the theory itself. So, physicists continue to test general relativity, looking for any crack, any tiny deviation that might point toward a more complete theory of gravity. Gravitational wave observations allow specific tests. One involves the speed of gravitational waves. General relativity unambiguously predicts they travel at the speed of light. Exactly. Alternative theories, especially those involving massive gravitons or extra fields, sometimes predict deviations. The observation of GW 170817, where gravitational waves and gamma rays arrived within 1.7 seconds after traveling for 130 million years, constrained the speed to be within 1 part in 10 to the power of 15 of the speed of light. This rules out many alternative theories outright. Another test involves dispersion. In general relativity, gravitational waves of all frequencies travel at the same speed, just like light in a vacuum. But if the graviton, the hypothetical quantum particle associated with gravity, has a tiny mass, different frequencies would travel at slightly different speeds, like light passing through a prism. By analyzing whether low-frequency and high-frequency components of a gravitational wave signal arrive at different times, physicists can place limits on the graviton mass. So far, the limit is incredibly stringent. If the graviton has mass, it's less than about 10 to the power of negative 23 electron volts, trillions of times lighter than any other known particle. Gravitational waves also test the nature of black holes. According to general relativity, Black holes are described completely by mass and spin, and theoretically charged, though astrophysical black holes are thought to be electrically neutral. This is the no-hair theorem. Black holes have no other properties, no hair, to distinguish them beyond these basic parameters. The ring-down phase of a merger provides a way to test this. If the final object is a Kerr black hole, its ring-down should consist of specific frequencies determined solely by its mass and spin. Any deviations might indicate the object isn't a black hole, or that general relativity needs modification. To date, every ring-down observed matches the predictions for a Kerr black hole. But as more events are detected, and as analysis techniques improve, these tests will become more sensitive. Future observations might detect subtle deviations that point toward new physics. Or they might continue to confirm general relativity, pushing alternative theories further into the margins. Either outcome is scientifically valuable. Beyond testing gravity itself, gravitational waves provide information about the population of compact objects in the universe. Before LIGO, we knew black holes existed, but we had only limited knowledge of their masses and how common they were. Gravitational wave observations have revealed a rich population of black holes across a wide mass range, from a few times the mass of the Sun to over 100 solar masses. The distribution of masses, the rate at which mergers occur, and the spins of black holes all provide clues about how these systems form and evolve. Some of the detected black holes are heavier than any previously known stellar mass black holes. This suggests either that stellar evolution can produce more massive black holes than once thought, perhaps in environments with low metallicity where stellar winds are weaker, or that some black holes grow through mergers. The presence of black holes in the pair instability mass gap strongly suggests hierarchical merging is occurring, where black holes collide multiple times over cosmic history. The spin distribution of black holes also tells a story. If binary black holes form from stellar binaries, where two stars orbit each other and both collapse to black holes, the spins should be preferentially aligned with the orbital angular momentum. If they form through dynamical capture in dense stellar clusters, the spins should be more randomly oriented. Current data show a mix, suggesting both formation channels contribute to the population. Gravitational waves also offer a new way to measure cosmic distances. The standard cosmological distance ladder relies on a series of steps, starting with geometric methods in the solar system, moving to parallax measurements for nearby stars, then to Cepheid variables, supernovae, and other standard candles whose intrinsic brightness is known or can be calibrated. Each step has uncertainties that propagate to the next, and different methods sometimes give slightly different answers. Gravitational waves provide an independent distance measurement. The amplitude of the signal depends on the masses of the merging objects and the distance to the source. From the waveform, you can determine the masses. Combining that with the observed amplitude gives the distance without needing any intermediate steps in a distance ladder. This method is sometimes called a standard siren, by analogy with standard candles. For black hole mergers, the standard siren method has challenges because you don't automatically know the redshift of the source. You'd need to identify the host galaxy, which requires precise sky localization and follow-up with electromagnetic telescopes. But for neutron star mergers, like GW170817, where an electromagnetic counterpart is detected, you can identify the host galaxy immediately and measure its redshift spectroscopically. This gives both distance and redshift, allowing a direct measurement of the Hubble constant. The current measurement from GW170817 has large uncertainties because it's based on a single event. But as more neutron star mergers are detected with electromagnetic counterparts, the method will improve. Within a decade or two, gravitational wave observations might provide one of the most precise and independent measurements of cosmic expansion, potentially resolving discrepancies between other methods and clarifying our understanding of dark energy. Gravitational waves also carry information about the state of the universe in its earliest moments, though we haven't yet detected these primordial signals. While current detectors focus on astrophysical sources like merging black holes and neutron stars, future detectors, particularly space-based ones like LISA, will be sensitive to lower frequencies where cosmological sources could become detectable. These would include gravitational waves from the Big Bang itself, ripples generated during cosmic inflation, and signals from phase transitions in the early universe. Detecting a stochastic background of primordial gravitational waves would be a monumental discovery, one that scientists have pursued for decades. Such waves would provide a window into processes that occurred when the universe was a tiny fraction of a second old. They would carry information about the inflationary epoch, the rapid expansion thought to have occurred immediately after the Big Bang, smoothing out the universe and setting the initial conditions for structure formation. They could reveal the energy, scale of inflation, and test different models of how inflation occurred. But for now, this remains a goal for future instruments, a tantalizing possibility rather than a confirmed detection. Even closer to the present, gravitational waves can probe the large-scale structure of the universe. As they travel through space, gravitational waves can be lensed by intervening galaxies and clusters, just like light. Strong lensing of gravitational waves might produce multiple copies of the same signal arriving at different times. Weak lensing causes subtle distortions in the waveform that are harder to detect, but contain information about the matter distribution along the line of sight. Future detections with highly sensitive instruments could use gravitational wave lensing to map dark matter and study the growth of cosmic structure. There's also the question of what gravitational waves can tell us about dark matter directly. While dark matter doesn't emit or absorb light, it does have mass, and mass affects spacetime. If dark matter is clumped into dense structures, like primordial black holes or ultra-compact mini-halos, those structures could interact with gravitational waves in detectable ways. Alternatively, if dark matter is made of exotic particles that interact weakly with gravitational fields, their presence might leave subtle imprints on gravitational wave signals. These are speculative ideas, but they illustrate how gravitational wave astronomy might eventually contribute to solving one of physics' deepest mysteries. Each gravitational wave detection is more than just an observation. It's a piece of evidence about how the universe works at the most fundamental level. It's a test of Einstein's century-old theory in regimes he could never have imagined. It's a measurement of the masses and spins of objects so dense that they defy earthly comparison. It's a probe of cosmic expansion, a window into the population of black holes across billions of years of history, and potentially a glimpse of the universe's earliest moments. The beauty of gravitational wave astronomy is that it reveals things invisible to light. Electromagnetic astronomy has given us an incredible wealth of knowledge about the cosmos, but it has limitations. Light can be absorbed by dust, scattered by gas, and can only carry information about electrically charged particles and their interactions. Gravitational waves, by contrast, pass through everything unimpeded. They respond only to mass and energy, not to charge or temperature. They bring us information from the darkest regions of space, from inside stellar cores and black hole mergers, from environments too extreme for light to escape. As detectors improve and more events are recorded, the picture will become clearer. We'll develop a statistical understanding of black hole populations, measure cosmic parameters with unprecedented precision, and perhaps, just perhaps, detect deviations from general relativity that point toward new physics. Or we'll continue to confirm Einstein's theory, marveling at how robust it is even under the most extreme conditions. Either way, we'll be listening to the universe speak in a language of pure geometry, in ripples of space-time itself, in the fundamental music of gravity. The future next-generation eyes on the cosmos. If the current generation of gravitational wave detectors has opened a new window on the universe, the next generation promises to blow the walls off entirely. The detectors being planned and designed for the 2030s and beyond will be so sensitive, so capable, that they'll detect events current instruments can barely glimpse. They'll reach back to the earliest moments of the universe, observe the collisions of supermassive black holes at the centers of galaxies, and catalog thousands or tens of thousands of mergers across cosmic time. The future of gravitational wave astronomy is not just bright, it's transformational. Current detectors, advanced LIGO, Virgo, and Kagra, are what we call second-generation instruments. The first generation, operational from 2002 to 2010, proved the concept but wasn't sensitive enough to detect gravitational waves. Second-generation detectors, with improvements in lasers, mirrors, seismic isolation, and quantum noise reduction, succeeded in making detections. But they operate at the edges of their design sensitivity. Third-generation detectors will push an order of magnitude further, increasing the volume of space they can survey by a factor of 1,000. In Europe, the Einstein telescope is the leading third-generation design. Rather than the L-shaped configuration of current detectors, Einstein telescope will be triangular, with 3 corners each housing interferometers with 10-kilometer arms. The entire facility will be built underground, roughly 200 to 300 meters below the surface, to reduce seismic noise and temperature fluctuations. 2 candidate sites are being evaluated, one in Sardinia, Italy, and one in the Euregio-Meuse-Rhine region spanning Belgium, Germany, and the Netherlands. Underground construction offers major advantages. Seismic noise at low frequencies drops dramatically with depth. Temperature variations that cause thermal expansion of the ground are greatly reduced. Isolation from human activity, traffic, and weather improves. The cost is higher, of course. Tunneling and excavating underground spaces is expensive, but the payoff in sensitivity justifies the investment. Einstein telescope will use advanced technology across the board. Some of the mirrors will be cooled to cryogenic temperatures, 10 to 20 degrees above absolute zero, to reduce thermal noise. Others will operate at room temperature, but with even better coatings and suspension systems than current detectors. The design uses something called a xylophone configuration, where 2 different interferometers are optimized for different frequency ranges, and their outputs are combined. An interferometer focuses on low frequencies, from a few hertz to about 40 hertz, using cryogenic mirrors and low-power lasers. The other targets higher frequencies, from 40 hertz to several kilohertz, with room temperature mirrors and high-power lasers. This dual approach allows Einstein telescope to be sensitive across a very broad frequency range, hearing both the early in-spiral of massive black holes at low frequencies and the merger and ring down of lighter objects at higher frequencies. The sensitivity improvement compared to current detectors is about a factor of 10 in strain amplitude, which translates to a factor of 1,000 in surveyed volume. If advanced LIGO can detect a binary neutron star merger out to about 200 megaparsecs, Einstein telescope will see such events out to 2,000 megaparsecs or more, covering a significant fraction of the observable universe. Across the Atlantic, the United States is planning Cosmic Explorer, an even more ambitious project. Cosmic Explorer will consist of 1 or possibly 2 L-shaped interferometers, but with arms 40 kilometers long, 10 times longer than LIGO's. A second site might have 20-kilometer arms. Unlike Einstein telescope, Cosmic Explorer will be built on the surface, leveraging decades of experience with surface installations, but using improved seismic isolation, better vacuum systems, and more advanced optics. The longer arms provide a straightforward sensitivity boost. Gravitational waves stretch and compress space along the length of the interferometer arms. The longer the arms, the larger the absolute displacement for a given strain. Since most sources of noise don't scale with arm length, Longer arms mean better signal-to-noise ratios. Cosmic Explorer's 40-kilometer arms will make it the most sensitive gravitational wave detector on the ground, able to detect stellar mass black hole mergers from the edge of the observable universe. Together, Einstein Telescope and Cosmic Explorer will form a global network of third-generation detectors. Operating simultaneously, they'll provide excellent sky localization for sources, enabling rapid electromagnetic follow-up for events like neutron star mergers. The improved sensitivity will increase the detection rate dramatically. Instead of a few hundred events per year, third-generation detectors will observe thousands, possibly tens of thousands of mergers annually. Binary neutron stars, currently rare in the detected population, will become common. Black hole mergers from across cosmic history will fill the catalogs. This flood of data will revolutionize our understanding of compact object populations. We'll trace the evolution of black hole mergers from the early universe to the present, seeing how merger rates change with cosmic time. We'll study the distribution of black hole masses and spins in detail, distinguishing between different formation channels. We'll detect intermediate mass black holes routinely, clarifying the connection between stellar mass and supermassive black holes. And we'll make precision measurements of cosmological parameters, using gravitational waves as standard sirens to map the expansion history of the universe. But third-generation ground-based detectors, as powerful as they are, have a fundamental limitation. They're sensitive primarily to frequencies above about 10 Hz. Below that, seismic noise, even with underground construction and advanced isolation, becomes overwhelming. Yet many of the most interesting gravitational wave sources emit at lower frequencies. Supermassive black hole mergers, those involving black holes millions or billions of times the mass of the Sun, produce signals in the millihertz to centihertz range. To observe these, you need a detector in space. Enter LISA, the Laser Interferometer Space Antenna. LISA is a collaborative mission between the European Space Agency and NASA, scheduled for launch in the mid-2030s. Unlike ground-based detectors, LISA won't be built on Earth. It will consist of 3 spacecraft flying in a triangular formation, with each side of the triangle measuring 2.5 million kilometers. That's roughly 100 times the distance between Earth and the Moon, making LISA's arms about 600 times longer than Cosmic Explorer's. The 3 spacecraft will orbit the Sun, following Earth in its orbit, but trailing about 50 million kilometers behind. The triangle slowly rotates as it orbits, maintaining its shape through precise control of each spacecraft's position. Lasers link the spacecraft, measuring the distances between them with picometer precision. When a gravitational wave passes through the constellation, the distances change slightly, and these changes are recorded. LISA will be sensitive to frequencies from about 0.1 MHz to 0.1 Hz, a completely different range from ground-based detectors. In this frequency range, the universe is full of sources. Supermassive black hole mergers at the centers of galaxies will be visible across the cosmos. Binary stars in our own Milky Way, especially compact binaries consisting of white dwarfs, neutron stars, or black holes, will produce continuous signals. Extreme mass ratio inspirals, where a stellar mass black hole spirals into a supermassive black hole, will trace the spacetime around the larger black hole with exquisite precision. LISA will also search for the cosmological gravitational wave background, ripples produced in the first moments of the universe that have stretched to low frequencies by cosmic expansion. Detecting this background would be a profound achievement, providing information about physics at energy scales far beyond what particle accelerators can reach. It would test models of cosmic inflation, constrain the properties of dark matter, and potentially reveal signatures of phase transitions in the early universe. One of LISA's unique capabilities is early warning. For binary systems consisting of stellar mass black holes that will eventually merge and be detected by ground-based detectors, LISA can see them years or even decades before the final merger. It will observe their slow and spiral at low frequencies, providing advance notice of when and approximately where the merger will occur. This will allow ground-based detectors to target specific regions of the sky, improving ski localization and enabling better electromagnetic follow-up. The synergy between ground-based and space-based detectors creates a comprehensive gravitational wave observatory network spanning 7 orders of magnitude in frequency. LISA covers the low-end, third-generation ground detectors like Einstein telescope and Cosmic Explorer cover the high-end, and together they'll observe everything from supermassive black hole mergers across the universe to stellar mass mergers in our cosmic neighborhood. Construction and launch timelines are ambitious. Einstein telescope aims to begin construction in the late 20s, with operations starting in the mid-2030s. Cosmic Explorer is on a similar timeline, though funding and site selection are still in progress. LISA's mission is already approved, with critical technology demonstrations completed by the LISA Pathfinder mission in 2016. The spacecraft are being built, and launch is planned for 2035 or shortly thereafter, with science operations beginning a few years later, after the constellation reaches its operational configuration. Beyond these major projects, other concepts are being explored. In Australia, there's interest in building a third-generation detector in the southern hemisphere to complement Einstein telescope and Cosmic Explorer. A global network of third-generation detectors, with at least one in each hemisphere, would provide optimal sky coverage and localization. At even lower frequencies, below LISA's range, lies another frontier. Pulsar timing arrays use radio telescopes to monitor the precise timing of pulses from millisecond pulsars scattered across the galaxy. Gravitational waves at nanohertz frequencies, corresponding to orbital periods of years, cause tiny variations in the pulse arrival times. These ultra-low frequency waves are likely produced by supermassive black hole binaries in the nearby universe. Recent results from pulsar timing arrays have detected hints of a gravitational wave background at these frequencies, opening yet another window. The progression from current to future detectors is not just about sensitivity. It's about completeness. With each new frequency range we access, we see different types of sources, different eras of cosmic history, different physical processes. Ground-based detectors reveal stellar mass mergers. LISA will show supermassive mergers. Pulsar timing arrays probe the ultra-low frequency background. Together, these instruments will build a comprehensive picture of gravitational wave sources across the universe. The science enabled by third-generation detectors is hard to overstate. They'll detect hundreds of thousands of mergers, providing statistical power to answer questions we can barely formulate today. They'll trace the formation and evolution of black holes from the first galaxies to the present. They'll test general relativity with unprecedented precision in the strongest gravitational fields. They'll provide independent measurements of cosmological parameters, potentially resolving current tensions between different methods. They'll discover new classes of sources we haven't predicted. And they'll do all this while inspiring the next generation of physicists and astronomers, showing young people that the universe still holds mysteries worth exploring. Funding these projects requires international cooperation and long-term commitment. The costs are substantial, billions of dollars or euros spread over decades. But the scientific return is equally substantial. Gravitational wave astronomy is not a luxury. It's a fundamental tool for understanding the universe, as essential as optical telescopes or particle accelerators. Every major advance in observational capability has revealed phenomena we didn't anticipate. There's every reason to believe that third-generation gravitational wave detectors will do the same. And beyond the science, there's inspiration. The idea that we can build instruments so sensitive they detect ripples in space-time from collisions billions of light-years away, that we can place 3 spacecraft in a perfect triangle, 2.5 million kilometers on a side, and measure distances between them to within trillionths of a meter, that we can listen to the universe and hear its deepest secrets. These are achievements that remind us of what humanity is capable of when we dedicate ourselves to understanding nature. The future of gravitational wave astronomy is not just about building bigger detectors. It's about building a community, training the next generation of researchers, developing new technologies that spin off into other fields, and fostering international collaboration on projects that transcend national boundaries. It's about asking questions we don't yet know to ask, and being ready to interpret answers we can't yet imagine. It's about continuing the journey that began with Einstein's equations in 1916, took a giant leap forward with the first detection in 2015, and reaches toward a future where gravitational waves are as routine and powerful a tool for exploring the cosmos as light itself. The ripple effect, transforming science and society. The impact of gravitational wave astronomy extends far beyond the immediate scientific discoveries. It's a story of technological innovation, international collaboration, public engagement, and the reshaping of how we understand our place in the universe. The ripple effect of detecting these cosmic whispers reaches into multiple domains, influencing everything from fundamental physics to engineering, from education to philosophy. Start with technology. Building. Instruments sensitive enough to detect gravitational waves required pushing multiple technologies to their limits and beyond. Lasers had to be stabilized to unprecedented levels, maintaining constant frequency and power over hours or days. The solution involved advanced feedback systems, thermal control, and novel optical designs. These techniques have found applications in other fields, from precision manufacturing to telecommunications. Mirror coatings and polishing techniques advanced dramatically. LIGO's mirrors are coated with thin layers of materials designed to reflect laser light with minimal absorption and scattering. The coatings must be uniform to within a few atoms thickness across surfaces 40 centimeters in diameter. The polishing must be so precise that surface irregularities are measured in nanometers. These advances have benefited other fields requiring ultra-precise optics, including semiconductor manufacturing and optical communications. Seismic isolation systems developed for LIGO use sophisticated, active, and passive damping to filter out vibrations across a wide range of frequencies. The technology has applications in any situation where sensitive measurements must be made, despite environmental noise. Some of these techniques have been adopted in precision manufacturing, where vibration can affect the quality of machine parts, and in construction, where buildings in earthquake-prone regions benefit from advanced isolation methods. Data analysis techniques developed for gravitational wave astronomy have broader applicability. Searching for weak signals buried in noise is a common problem across science and engineering. LIGO developed advanced matched filtering algorithms, machine learning approaches for signal classification, and methods for dealing with non-Gaussian noise. These techniques are now being applied to other fields, from analyzing medical data to monitoring infrastructure for signs of degradation. The computational challenges are immense. Numerical relativity simulations require supercomputers running for months to model a single merger. Parameter estimation from detected signals involves exploring vast parameter spaces, comparing observed data to millions of theoretical waveforms. Maintaining and analyzing the continuous data streams from detectors generates petabytes of data that must be processed, stored, and made accessible to researchers worldwide. These challenges have driven innovations in high-performance computing, distributed computing, and data management. But technology is only part of the story. Gravitational wave astronomy has fostered an extraordinary level of international collaboration. The LIGO scientific collaboration and Virgo collaboration together include over 1,500 scientists from more than 100 institutions in 20 countries. These researchers work together seamlessly, sharing data, dividing analysis tasks, and jointly authoring papers. The collaboration model has become a template for how large-scale scientific projects can be organized and managed. This collaboration crosses not just national borders, but disciplinary ones. Gravitational wave research brings together experimentalists and theorists, observers and modelers, astrophysicists and nuclear physicists, engineers and software developers. A single detection involves contributions from people working on optics, seismic isolation, data analysis, theoretical waveform modeling, electromagnetic follow-up observations, and more. The interdisciplinary nature of the field enriches it, bringing diverse perspectives and expertise to bear on complex problems. The field has also pioneered open data policies. In 2018, LIGO and Virgo made their data publicly available through the Gravitational Wave Open Science Center. Anyone, anywhere, can download the data and analyze it. This openness has several benefits. It allows independent verification of published results, increasing confidence in the findings. It enables researchers who aren't part of the collaboration to explore new analysis methods or search for signals the main collaboration might have missed. And it provides valuable data sets for education, allowing students to work with real data from cutting-edge experiments. Public engagement has been a priority from the beginning. The first detection was announced at press conferences broadcast worldwide. Visualizations of merging black holes and animated waveforms helped people understand what gravitational waves are and why they matter. Outreach programs bring the science to schools, museums, and public forums. LIGO hosts open houses where visitors can tour the facilities and meet scientists. These efforts make cutting-edge physics accessible and exciting to non-specialists. The discovery of gravitational waves resonated with the public in part because it's a fundamentally human story. It's about curiosity, about wanting to understand the universe, about not giving up even when problems seem insurmountable. It's about hundreds of people dedicating their careers to a goal that many thought impossible. And when that goal was finally achieved, when the first chirp was heard, it was a victory not just for science, but for human persistence and ingenuity. Educational programs at all levels have incorporated gravitational wave astronomy. University courses now include modules on gravitational waves, interferometry, and data analysis. High school students learn about the discoveries and the physics behind them. Interactive exhibits in museums demonstrate how gravitational waves stretch and squeeze space. These educational efforts inspire the next generation, showing young people that physics is not a closed book, but an ongoing adventure with new discoveries still to be made. Philosophically, gravitational wave astronomy reminds us of our connection to the universe. The atoms in our bodies were forged in stars. The gold in our jewelry came from neutron star mergers, and now we can hear those mergers happening, can detect the ripples they send through spacetime. We're not just observers of the cosmos. We're part of it, connected through physics and chemistry, through the fundamental forces and particles that make up everything. There's also a sense of humility. The universe is vast, ancient, and full of phenomena far beyond everyday experience. Black holes merging billions of light years away, neutron stars compressing matter to densities we can barely imagine, gravitational waves carrying messages across cosmic voids. These discoveries remind us how small we are, how brief our existence on the cosmic timescale, and yet how remarkable it is that we can understand even a little of this vast reality. Economically, gravitational wave research has impacts too. Large-scale scientific projects create jobs, from PhDs analyzing data to technicians maintaining equipment. They drive demand for high-tech manufacturing, spurring innovation in industry. Companies that develop technologies for gravitational wave detectors often find other applications for those technologies, leading to commercial products and spin-off companies. The economic multiplier effect of such research is well documented, with every dollar invested in basic science generating multiple dollars in economic activity over time. And there are intangible benefits. A society that values science, that invests in understanding nature, that celebrates discoveries like the detection of gravitational waves, is a society that looks forward. It's a society that believes in progress, in the power of knowledge, in the ability of humans to solve complex problems through reason and evidence. These values matter, especially in an era when science literacy and trust and expertise are challenged. Gravitational wave astronomy also serves as a model for addressing global challenges. Climate change, pandemics, resource depletion. These are problems that require international cooperation, long-term thinking, and the application of scientific knowledge. The success of gravitational wave collaborations shows that such cooperation is possible, that researchers from dozens of countries can work together toward common goals, that national differences can be set aside in pursuit of shared understanding. If we can build gravitational wave detectors together, perhaps we can tackle other challenges together too. The philosophical implications run deeper still. For most of human history, gravity was simply the force that made things fall, that kept us anchored to the Earth. Newton gave us equations to describe it, but even he admitted he didn't know what caused it. Einstein showed us that gravity isn't a force at all, but a feature of curved spacetime, a fundamentally geometric phenomenon. Gravitational waves make this tangible. They're literal ripples in the fabric of reality, waves in space and time themselves, not waves traveling through space, but waves of space. This is profound. It means that the stage on which everything happens, the background we think of as empty and unchanging, is neither. Space-time is dynamic, flexible, responsive. It can be bent by mass, rippled by acceleration, twisted by rotation. And we can measure these effects, can listen to space-time vibrating. In a sense, gravitational wave astronomy is the most fundamental form of astronomy because it observes the substrate of existence itself. The journey from Einstein's prediction to the 200th detection has been long, winding through decades of doubt and development, through technological challenges and theoretical puzzles. But it's also been triumphant, demonstrating that persistence pays off, that seemingly impossible goals can be achieved, and that the universe still has secrets to reveal. Each detection is a gift, a message from the cosmos, a reminder that reality is stranger and more beautiful than we often imagine. As we look to the future, to third-generation detectors and space-based observatories, to thousands of detections per year and discoveries we can't yet predict, we carry with us the lessons of this journey. That curiosity drives progress. That collaboration amplifies our capabilities. That technology developed for fundamental research benefits society in countless ways. And that the universe, for all its vastness and complexity, is not beyond our ability to comprehend. The ripples detected by LIGO and Virgo are not just scientific data. They're connections to the deep past, to events that occurred billions of years ago in galaxies far away. They're tests of our deepest theories about how reality works. They're inspirations for the next generation of scientists and engineers. They're reminders of our place in the cosmos, both humbling in the face of immensity and empowering in our ability to understand. And they're just the beginning. Closing, the Symphony of Spacetime. Now, let the weight of these discoveries settle gently around you. But before you drift off completely, there's one final revelation that ties everything together, one last twist that makes this story even more extraordinary than it already seems. Remember that opening moment? September 14th, 2015, when something impossible happened and your atoms moved by less than the width of a proton? Here's what makes that moment truly remarkable. It wasn't unique to you. Every person on Earth experienced it at the exact same instant. Every building, every mountain, every ocean, every living thing stretched and squeezed together in perfect synchrony. For 1/10 of a second, the entire planet moved as one, responding to an event that happened 1.3 billion years before humans existed, before Earth formed, before our sun ignited. And it's happening right now. As you read these words, gravitational waves from dozens of black hole mergers occurring at this very moment in distant galaxies are passing through you. Some from collisions happening a billion light years away. Others from events 10 billion light years distant. Your body is vibrating with the echoes of cosmic violence you will never see, from places you can never visit, carrying information about a universe far vaster and stranger than everyday experience suggests. This is what gravitational wave astronomy has truly given us. Not just data about black holes and neutron stars, but a visceral connection to the cosmos itself. Feel the day receding, the urgencies fading, as you contemplate what we've explored together. From Einstein's desk in 1916 to the control rooms of LIGO in 2025. From doubt and uncertainty to 200 confirmed detections. From the first whisper of GW 0914 to the monster black holes weighing hundreds of times more than our sun. From silent black hole collisions to neutron-star mergers that forge gold and platinum. From tests of general relativity to glimpses of the universe's earliest moments. From current detectors on Earth to future observatories in space. The story of gravitational wave astronomy is many things. It's a story of human achievement, of what we can accomplish when we set ambitious goals and refuse to give up. It's a story of the universe itself, of black holes and neutron stars, of spacetime bending and rippling, of cosmic violence transformed into gentle waves that wash over us, carrying information from the deepest past. It's a story of discovery, not just of new phenomena, but of new ways to observe, new methods to understand, new questions to ask. But perhaps most fundamentally, it's a story about listening, about paying attention, about developing the sensitivity to hear what the universe has been saying all along. Gravitational waves have been crossing the cosmos since the first black holes formed, since the first neutron stars collided, since the moments after the Big Bang itself. They've been passing through Earth, through every generation of humans, through dinosaurs and trilobites, through the formation of our planet, and the birth of our sun. Always there, always present, always carrying their messages. We simply couldn't hear them. Until we could. Until September 14th, 2015, when instruments built by thousands of people over decades finally became sensitive enough to feel space-time itself vibrate. And in that moment, a 100-year search ended, and a new era began. We learned to listen in a new way. We developed a new sense, neither sight nor hearing, but something unique. The ability to detect and interpret the stretching and squeezing of space itself. Since then, the universe has been speaking to us regularly. Twice a week on average, another signal arrives. Another black hole merger. Another whisper from billions of years ago. Another confirmation that the cosmos is alive with these events. The 200th detection on March 19th, 2025 was remarkable, not because it was unique, but because it was routine. Because it represented how far we've come. From hoping for one detection to cataloging hundreds. From uncertainty to confidence. From dream to reality. Each detection tells a story. 2 black holes, 85 and 66 solar masses, merging in the pair instability gap where they shouldn't exist. A 225 solar mass remnant spinning near the maximum allowed by physics. 2 neutron stars colliding 130 million light years away, producing a kilonova visible in light, forging heavy elements that would eventually seed new planets and perhaps new life. A signal from 15 billion light-years away, traveling through expanding space for 10 billion years before reaching our instruments. Each one unique, each one teaching us something new about the universe. And this is just the beginning. Third-generation detectors will be 100 times more sensitive. Space-based observatories will open entirely new frequency ranges. Within a few decades, we'll detect thousands of events per year. We'll catalog black hole mergers from the edge of the observable universe. We'll watch supermassive black holes colliding at the centers of galaxies. We'll search for gravitational waves from the Big Bang itself. The flood of discoveries will reshape astrophysics, cosmology, and fundamental physics. But even as we look forward to what's coming, take a moment to appreciate where we are. Right now, at this moment in history, gravitational wave astronomy is a mature field. We're no longer asking whether we can detect these waves. We know we can. We're asking what they tell us about black holes, neutron stars, the equation of state of ultra-dense matter, the expansion of the universe, the nature of gravity itself. These are questions of what and how, not if. That's a profound shift, and it happened in our lifetime. Many of the scientists who proposed and built LIGO are still active, still analyzing data, still pushing the field forward. Students who learned about the first detection in classrooms are now researchers contributing to the analysis of the 200th. The transformation has been rapid, generational, a once-in-a-century opening of a new window on the cosmos. So as you drift toward sleep, as your mind softens and your breathing slows, carry with you this image. The universe is singing. All around you, at every moment, space-time is rippling with the echoes of cosmic collisions. Black holes are merging in distant galaxies, sending waves that cross billions of light years before reaching Earth. Neutron stars are spiraling together, their final moments approaching. And on our small planet, in carefully constructed facilities, in Louisiana and Washington, in Italy and Japan, lasers are bouncing between mirrors, measuring distances to impossible precision, listening for these whispers from the void. You are part of this story. The atoms in your body oscillate slightly as gravitational waves pass through. By an amount too small to feel, too small to measure, without sophisticated instruments, but real nonetheless. You're connected to these cosmic events, linked by physics, to black holes merging when the universe was young. And through the work of thousands of scientists, through decades of development and discovery, we can now hear these connections, can translate the stretching of space-time into waveforms on screens, into numbers in databases, into knowledge about the universe. The 200th detection is a milestone, but not a destination. It's a marker on a journey that continues into the future. A journey toward understanding not just the phenomena we observe, but the fundamental nature of reality. Toward comprehending gravity in its strongest regimes, space-time in its most extreme states, the universe in its earliest moments. Toward building a complete picture of how black holes form and evolve, how neutron stars forge the heavy elements we depend on, how cosmic structure grows from tiny quantum fluctuations into galaxies and clusters. And in this journey, there's room for wonder, room to marvel at what we've achieved, at the instruments we've built, at the signals we've detected, room to appreciate the beauty of Einstein's equations, which predicted all of this a century before it was observed. Room to feel awe at the universe itself, at its vastness and violence, its order and chaos, its capacity to generate phenomena so extreme they warp the fabric of reality. If these explorations have brought you calm, if they've given you a peaceful way to end your day with curiosity rather than anxiety, consider subscribing. New journeys await, new topics to explore. new cosmic mysteries to contemplate as you drift towards sleep. But for now, rest. Let your mind wander through the stories we've told. Black holes dancing in the dark. Neutron stars colliding in brilliant colonovae. Spacetime rippling with waves from events so distant and ancient they seem almost mythological. Yet they're real, detected and measured, understood through mathematics and physics. The universe has been singing all along. We've only just learned to listen. And what we're hearing, what we continue to hear with each new detection, is the fundamental music of existence itself. The symphony of space-time, written in ripples and vibrations, in the stretching and squeezing of space, in the collision and merger of objects so massive they bend reality around them. It's a symphony that's been playing for billions of years and will continue playing for billions more. And now, finally, we can hear it. Sleep well. Dream of black holes and neutron stars, of detectors measuring the unmeasurable, of humans reaching across the cosmos with instruments of incredible sensitivity to touch the fabric of space-time itself. Dream of the 200th detection and the thousands more to come. Dream of Einstein, who predicted it all, and the engineers and scientists who made it real. And know that even as you sleep, even as your consciousness fades into rest, the universe continues its ancient rhythms, sending wave after wave through the darkness, ripples of reality spreading across the cosmos, carrying stories for anyone willing to listen. Good night, and may the cosmos sing you gently into dreams.